Yes, yes. We know you can start
You
the
know,
session.
can
Okay,
start the session.
okay, we'll start. So, good evening and welcome to fifth day of a SPARC online workshop on CO2 refrigeration system, fundamentals, advancements, and applications. As mentioned in previous workshop, today we have three sessions. For first session, I am pleased to welcome Dr. Pradeep Gupta. Dr. Pradeep Gupta is currently a postdoctorate fellow at the Indian Institute of Science, Bengaluru. In collaboration with NTNU Norway, he is exploring the feasibility of ejector-based transcritical CO2 refrigeration system for big shopping complexes and pharmaceutical industries. He earned his PhD in energy research and master in mechanical engineering from Indian Institute of Science, Bengaluru. During his PhD, he studies the performance and mixing characteristics of supersonic ejectors experimentally and numerically. At present, he authored 3 journal papers and presented 10 national international conference papers. So I request Dr. Pradeep Gupta to proceed with the presentation on ejectors and their relevance in CO2 cooling and heating application units.
Yeah, thank you, Vinod. I'll just share my screen. So yeah, is the screen visible?
Yes, yes.
Okay. So thank you, Vinod, for the introduction. And I'm Pradeep Gupta, a postdoctoral fellow at Indian Institute of Science, Bangalore, in collaboration with Norwegian Ministry of Science and Technology and TNU. So I'm going to speak about ejectors and their relevance in CO2 cooling and heating units. So in the previous talk, almost all the talks we had heard about the ejectors and the application of ejector in TCO2 systems. And we have seen this how ejector benefits the system to improve the performance of the particular system. So in this talk, mainly I'll speak about ejector, their working principle, and what are different category of ejectors and the different application in the refrigeration system, especially to the CO2 cooling and heating unit. So this is the contents, how I'll do in my presentation. So this presentation has been divided basically in 3 parts. In the first part, I'll explain the supersonic ejector, various application of ejector, and experimental results with the air ejectors, what we have conducted in IISc Bengaluru. Then what are the different parameters that affects the ejector performance and in turns the system performance. A brief analysis on the two-phase ejector, because ejector applied in the CO2 systems mostly though in two-phase region. Then part 2 is almost covered in various aspects by the different speakers, the importance of CO2 as a refrigerant, clean cooling CO2 as a working fluid, and modification to a standard system. So I just rush through these slides. And in the part 3, I'll explain what are the different systems where we can use ejectors, and ejector-based booster system, hybrid system, and the two-stage ejector refrigeration system. Then I'll conclude my talk with the summary and references. So now we start in with the supersonic ejector. So ejector is that device where two fluid, one at high pressure and that refrigerant coming from the dash cooler, which has pressure, very high pressure, that mixes with the low pressure fluid, which is coming from the evaporator. The CO2 or any refrigerant from the dash cooler or the condenser accelerate in the CD nozzle, the converging diverging nozzle, to the supersonic velocity in the nozzle. That creates the low pressure region in the suction chamber, which allows secondary flow to suck inside the ejector. Then the primary and secondary flow meets in that. And if the mixed flow is in supersonic region, that will produce a short structure because of the back pressure in the downstream of the ejector. Then the this normal short or the short structure turns the flow from supersonic to subsonic, and that expand the diffuser for the pressure recovery. So in this case, we can see here the schematic shows that nozzle operates in the under-expanded this. That's why we can see the primary flow expands further even after exiting from the nozzle, and that allows secondary flow to accelerate in this region. So we'll see these flow structures in following slides in details. The ejector works on the thermal principle of compression. That means it does not require any electricity or high-grade energy to produce the compression effect. It's only depend upon the mixing of the primary and secondary flow. Ejector does not consist of any moving part and hence required less maintenance. In addition, we can see this geometry or the construction of the ejector is very simple. This is just conversion diversion depth. Owing to these advantages, ejector has been used in various applications, starting from the aerospace application like pulse detonation engine, scramjet and ramjet engines, high altitude test facility, high speed wind tunnel testing, thrust automation, and jet noise suppression. In addition, ejector also has been applied in various energy applications like supercritical CO2 power system, transcritical CO2 refrigeration system, waste heat recovery, power plant vacuum generation, and the fuel cell anodic recirculation. So I have a slide schematic to just explain about the various application of ejector in energy sector. So in the first schematic here is that vapor ejector refrigeration system, where we are replacing the mechanical compression of the conventional refrigeration system by ejector, generator, and the liquid refrigeration pump. Here we have only a component which is moving, which has moving part and requires the power. And the power required by this compressor is, power required by this pump is almost about 10% than what we required in the mechanical compressor for the same cooling capacity. So we can, using this system, we can reduce the dependency on the electricity to drive this refrigeration system. The transcritical CO2 refrigeration system, anyway, this system again I'll explain in the later slide. So here I just mentioned that ejector in this case used as the expansion device, which reduces the irreversibility in the throttle valve. So we'll first expand the dash tuller CO2 from very high pressure to the low pressure, and then we'll throttle to the respective evaporator pressure. In the third case, when this system is like utilizing the waste heat rejected from the conventional VCRS system to drive the VERS system. In the power plant, ejector has been used as the removing or shutting the condensable gases from condenser to maintain the lower pressure in the condenser, such that we can extract more power from the turbine. In the fuel cell anodic recirculation, ejector has been used to utilize unburned hydrogen from the anodic cell. So normally we'll provide SS hydrogen in the fuel cell step for the proper mixing of the air with the hydrogen. So the unburned hydrogen will be purged into the atmosphere if you are not using ejector. So we are using ejector to just set the unburned hydrogen to improve the efficiency of the fuel cell steps. Now moving to the different classification of the ejector. So ejectors has been categorized based on different parameters like nozzle position. So when primary nozzle is placed inside the constant area section, it is called the constant area ejector. When it is nozzle is placed in the suction chamber, it is called CPM ejector. So these two ejector classification I'll explain in the later slide with the schematic. The nozzle design. So nozzle can either be convergent or convergent divergent. So in the previous slide, we seen this convergent divergent nozzle, where the primary flow is accelerated to the supersonic velocity. But in some cases, nozzle can be convergent as well. In that case, the primary flow Mach number or the speed of the primary flow is restricted to the sonic speed. So it enables though in the supersonic velocity, and that ejector called as a subsonic ejector. Based on the number of phases, ejectors are classified as 4 different categories. Like if primary and secondary both are in vapor phase, so we call as a vapor phase ejector. When primary, secondary are in liquid, so eject also will be in liquid, then ejector called as a liquid jet ejector. When the primary is vapor, secondary is liquid, and the exit flow is liquid, then we classify as a condensing ejector. And in this case, the vapor in the primary flow expand in the primary nozzle and produces the strong condensation shaft in the diverging portion of the primary nozzle. In the last one, when the primary flow is liquid, secondary is vapor, and exit flow is two-phase. So the ejector is classified as a two-phase ejector, and the shaft waves are possible based on the geometrical and operating parameter for these cases. So now this is the schematic of constant area mixing and constant pressure mixing ejector. So here we can see the nozzle is placed very close to the constant area section. Sometimes it also placed inside the constant area section. And it is expected that the complete mixing of the primary and secondary flow has to occur in the constant area section itself. While in case of constant pressure mixing, the nozzle is placed well inside this convergent duct, and the convergent duct is designed such a way that the mixing of the primary and secondary flow occurs at the constant pressure, and thus the name is constant pressure mixing ejectors. In these two cases, we can see we have the normal shaft or the shaft structure, this very within at the diffuser, and that charges the losses. So this AMS has developed or introduced and is kind of ejector where he has designed the diffuser such that the normal shaft cancelled out in the diffuser. So it recovers, or the back pressure for these ejectors are higher compared to these two ejectors. Now this is that just GIF for how ejector works. So the primary flow comes inside the nozzle and it's choked at nozzle throat, then it's accelerated to the supersonic velocity, and it's bulges out because of the under expansion that creates a secondary flow to choke at this point. Then the mixing starts. Mixing completed, and the complete mixing is a supersonic flow, so it expands further in the diffuser, and then it produces a shaft that turns the flow to the subsonic, and subsonic flow expand in the diffuser for the pressure recovery. Now, as I mentioned that secondary flow may or may not choke inside the nozzle, inside the ejector. Based on that, we classify the ejector operation as critical flow region and the mixed flow region. In the first schematic, the primary flow is anyway choked at the nozzle throat, and due to the under expansion of the primary flow expands further after exiting the nozzle, and it creates the converging portion for the secondary flow, where secondary flow accelerates and reaches to the reaches to the sonic condition somewhere in the mixing duct. So since both flows reach choke in this phase, they attain their maximum mass flow rate, and the performance parameter, which is the increment ratio, this is defined as the secondary mass flow rate to the primary mass flow rate, remain constant for these flow region. On the other hand, for the mixed flow region, only primary flow chokes at the nozzle throat, while secondary remains unchoked in the ejector. Increasing the back pressure causes secondary mass flow rate to decrease, and in turns the increment ratio with decrement in the increment ratio with the compression ratio. Reverse flow is like when primary flow itself is not choked and primary flow can come out from the secondary inlet, and that is called ejector fails. Now this is the experimental setup at laboratory for hypersonic and shaft wave research, IISc Bengaluru. So here we had tested just ejector, not the complete system. So we need to produce high pressure gas, and we have the screw compressor which can generate pressure up to 12 bar, and we have the VFD and the dry air dryer to produce in dry compressed air stored in the pressure vessel. So from pressure vessel, the high pressure gas is sent to the ejector via this primary nozzle, and the secondary flow is sucking from the ambient always. These two fluid mix in the mixing duct, and then they eject to the atmosphere again. And we have arrangement for the Slurrin measurement. This purple outline component shows the Slurrin images, and this blue one anyway, this is me-startrin. So I'm not going to explain anything about the me-startrin images. And these dots corresponds to the pressure ports along the ejector axis. So we have total 19 pressure ports, and we have 3 different rows. So to measure the primary and secondary pressures inside the ejector. So now this is that Selenium images for the critical flow region and the mixed flow region. So we can clearly see in this region the compression shaft, what we define as a recompression shaft. That indicates the flow is supersonic towards the end of the mixing that, and that in turn indicates that secondary flow shows somewhere in the mixing that. The location of secondary flow is still unknown, and it's open question. On the other hand, in the mixed flow region, we have not observed any decompression shaft, and it indicates that flow is subsonic after the mixing, and directly the pressure recovery takes place. So we'll see this performance characteristics of the based on the mass flow rate measurement and the pressure measurement also for the mixed flow region and critical flow region. So this graph anyway, I already explained with the schematic that constant increment ratio correspond to the critical mode operation, and this reducing increment ratio is a characteristic of the mixed flow region. It is also just noted here that wherever fill symbol that corresponds to critical mode operation, and the open symbol corresponds to the mixed mode operation, and that is consistent throughout the slides. So just consider this critical mode operation, where we can see this 2 dips in the pressure profile. As I mentioned, this in critical mode operation, the primary as well as secondary flow need to choke, and primary flow has to accelerate or the expand till the secondary flow choking pressure, which is significantly lower, and we can see the dip in the pressure. The primary flow and secondary flow mix, that is that attributed in this pressure profile as a rise in the pressure. And when the mixed supersonic flow expand further in the diffuser section, we can see a significant dip again, and this rise in pressure correspond to the recompression shaft in the diffuser section. After that, this flow turns to the subsonic, and we have the gradual pressure rise in the diffuser part. On the other hand, for the mixed flow region, primary flow expansion is not significant, so we do not see any pressure dip in this profile. So this continuous rise in pressure correspond to the mixing of the primary and secondary flow, and this gradual rise corresponds to the pressure recovery in the diffuser section. So now these are the parameters which these first 2 are the performance parameter of the ejector called the increment ratio. I explained this, which is defined as the secondary mass flow rate to the primary mass flow rate. Compression ratio is defined as the exit pressure to the secondary stagnation pressure, and that is the measure how much compression effect we can get from an ejector. These are the influencing parameter called the stagnation pressure ratio, which is defined as the primary stagnation flow pressure to the secondary stagnation flow pressure. And area ratio is defined as the ratio of the mixing that area to the nozzle throat area. Here we had used rectangle nozzle, so just I multiply with the W, which is the width of the ejector, and small w is the width of the nozzle. The nozzle area ratio is defined as that nozzle exit area to the nozzle throat area, and mixing that length to height ratio is L by H. So I'll in my slides I have covered the effect of these 4 parameters. Other than that, the NHP also affect the ejector performance, and the component efficiency also affects the ejector performance. That I'll just show the the literature results, not my results. So here we can see the effect of the stagnation pressure ratio on the ejector performance. So we have in our experiment we had. Yes, someone has a question.
No, Pradeep. No, Dr. Pradeep. You go ahead.
Okay, fine. So we had varied the stagnation pressure ratio from 5.49 to around 10, and a few Selenium images are shown here. So first thing we can see here that if we increase this stagnation pressure ratio, the increment ratio decreases. That because of 2 reasons. First reason, increase in the SPR corresponds to the increase in the primary flow, because primary mass flow rate is directly proportional to the this primary stagnation pressure, and in this case secondary flow is coming from atmosphere, so SPR increment directly attributed to the primary flow, primary stagnation pressure increment. The other case, we can closely look on the nozzle exit vicinity of the nozzle exit. So we can see as we increase this SPR, the primary nozzle start operating in severely under expanded flow, and that restrict the secondary flow path. The critical area for secondary flow decreases, so that reduce the secondary mass flow rate. So the combined effect of the reduced secondary mass flow rate and the increased primary mass flow rate resulted the detriment in the increment ratio if we increase this SPR value. This pressure profile, we can see the two depths, and that corresponds to the critical mode operation of these ejectors at different SPR conditions. So we can see the recompression shaft and two depths in the pressure profile. Now moving on the primary nozzle, the geometry of the primary nozzle. So we had used three different primary nozzle, which have the design Mach number of 1.5, 2.0, and 2.5. So in these cases, since the nozzle exit height is same at 6 mm, we had changed the nozzle throat height to achieve this different Mach number nozzle. So the Mach number of 1.5 has the greatest nozzle throat height, means it has the greatest primary mass flow rate. And also we can see the nozzle with 1.5 Mach operates in the severely under expanded, so it has the lower secondary mass flow rate. That we can see here that the ejector with nozzle Mach number of 1.5 has the least increment ratio. As we increase this nozzle operation shifted from the under expanded to over expanded for Mach number 2.5. And these dip in the pressure profile and recompression shaft in these cylinder images indicates that these ejectors operate in the critical mode operation. So the effect of area ratio is defined as that matching that height to the nozzle throat height. So we can alter the area ratio by either changing this matching that height or changing the nozzle throat height. So we have three different ejector, 4, 7, and 8, and along with the three different nozzles, nozzle 1, 2, and 3. So we have total 9 data points for the to observe or to study the area ratio on the ejector performance. So here in these plots, again we just noted that this filled symbols corresponds to the critical mode operation, and unfilled symbols corresponds to the mixed mode operation. So we consider this nozzle 1, and these three circles corresponds to the ejector 4, 7, and 8. So we'll we'll just consider this only one series of nozzle 1. So we'll see increasing the area ratio or increasing the mixing that height of the ejector increases the increment ratio, though the ejector operation shifted from critical mode operation for ejector 4 to the mixed mode operation for ejector 7. Region here, and since we are considering the nozzle 1, so the primary mass flow rate remain constant for these series. So the increment in the increment ratio directly attributed to the increment in the secondary mass flow rate. So here changing from ejector 4 to 7, we are increasing the mixing that height. That increases the area available for the secondary flow. Even the velocities for ejector 4 to ejector 7 decreases, but the area increment is dominated over the velocity increment. That's the reason we are having the higher increment ratio. That will be clear when we'll see the cylinder images. And further increment in the mixing that height resulted in the detriment in the increment ratio. Here again the velocities of the secondary flow becomes very low, and that resulted the lower increment ratio. Here in the pressure profile, we'll see for ejector 4 only we have two dips in the pressure profile. That corresponds to the critical mode operation of this ejector or ejector 4, while the ejector 7 and 8 operates in the mixed mode operation. So we can see again here we only have the recompression shaft for ejector 4, And for ejector A7, even we can see the secondary mass flow, secondary velocities are bit high, but in case of ejector A, the secondary velocity is very low, and that resulted the lower increment ratio for ejector A. So now the mixing duct length, variation of the mixing duct length and the ejector performance. So we have 6 different ejectors having the L by D ratio of or L by H ratio of 1.67 to 20. So we had a broad range to study the mixing duct length effect on the ejector performance. Here, this graph again shows that ejectors operates in the the ejector operates in the trickle mode operation, since we have the constant increment ratio followed by the decrement in the increment ratio. This increment ratio versus L by H plot shows here till L by D ratio of 1 to 10, the increment ratio is almost constant considering the measurement uncertainty. The region of constant increment ratio lies in the mixing characteristics of the ejector that I am not going to explain here, but we can say that non-mix length, which is the mixing characteristics of these ejectors, that is around 10 times of the L by H for these ejectors. And that region, there is no significant change in the increment ratio when the mixing duct length is less than that non-mix length. In region beyond that, we have seen increment in the increment ratio that that is due to the proper mixing of the primary and secondary flow in the later part of the mixing duct. Further increment in the mixing duct resulted in the lower increment ratio that resulted because of the increased frictional effect that then will be explained properly with the slurry images. This plot shows that we have the dips in the pressure profile and ejector operates in the critical mode operation. So here we can see here there is a no mixing duct length, or mixing duct length is only about height of the this mixing duct. So still we can see the short structure in the diffuser. This also we can see short structure in diffuser and other these nozzles. And closely looking on ejector 5 and ejector 6. So we can see the short strength of the ejector 5 is minimal, while increasing the length from 180 mm to 240 mm. The strength of the shot has increased. That is due to the frictional choking of the the high length, or this length is longer than the frictional length required for the choking. Now this is all for the air ejector, but most of the time when we use ejector in the refrigeration system or the ejector as an expansion device, where ejector will be in the two-phase region. So we need to just look on the how we can analyze the ejector when it's in two-phase region. So this is a simple nozzle where vapor is start accelerating in the nozzle, and it started nucleation at the nozzle throat. The bubble start growing inside this diffuser section, and it reaches the critical bubble size. Then the bubble started and different sizes in the mixing duct or in the suction chamber. So this Lee et al. Has measured the pressures at 4 different points inside the nozzle. So A is in the converging portion, B at the throat, and C and D are in diffuser section. And we can see the pressure variation inside the nozzle at different axial location. This graph shows that the eject dryness fraction based on the different primary flow pressure. So to analyze the ejector, there are 2 models. The homogeneous equilibrium model and homogeneous relaxation model is well studied in the literature. So in HEM model or homogeneous equilibrium model, we assume this dryness fraction to the thermodynamic equilibrium quality that is defined as H minus HL by HV minus HL. While in homogeneous relaxation model, we'll get actual actual quality, and these local properties are defined based on the pressure and the actual the quality of the system, quality of the flow. Now the speed of sound calculation in two-phase is more important when ejector operates in the critical mode. There the secondary flow has to choke, and we need to know the velocity, that is the boundary condition for the critical mode operation. So There are two models given for the speed of sound calculation. One is based on the HRM model and one is based on the HEM model. So it is reported that HRM model provides around 15% better results than HEM model. So we just use these equations, and that is taken from these references. This alpha here is a wide fraction, ST is the slip ratio, and K is a constant which has a value of 0.4 for best fit. Now moving to the transcritical CO2 refrigeration system, or the feasibility of CO2 system as a refrigerant. So I think most of the slides have been spoken about this. So just rushing these slides. So we know that GWP is 1, OTP is 0. It classified as A1 refrigerant, means it's non-flammable and non-toxic. It has a stable chemical property and non-corrosive. The volumetric efficiency of CO2 is much higher as compared to the other refrigerant. So I think this should be not 744. This is some other fluid area. This is in low temperature and this is high temperature. So this has a very high volumetric capacity that reduces the system size and the material cost as well. Now this also has been explained. This is subcritical mode and the transcritical mode. So I want to highlight here is that in transcritical mode, the approach temperature is around 5 to 7 degrees Celsius, while in transcritical it is very close, around 2 to 3 degrees Celsius. So this is the advantage, and limitation also we know that we need to the systems experiences high pressure and the control issue would be in the transcritical mode. So this also mostly has been explained. So this is a standard system where we have the main compressor, the Aspula throttle valve, flash tank, and expansion valve evaporator. So we are using this internal heat exchanger, and this already has been explained in great detail in previous talk. We are using parallel compressor also to improve this cycle efficiency. This also has been explained. So our main focus on the ejector-based system, so that I'll explain in the following slides. Now, these are a comparison of the transcritical basis system, parallel system, and the parallel system with an injector. So transcritical system is less efficient or more efficient till 27. If the environment goes up, it is lower compared to R404A, and that is around -11%. Parallel systems are more efficient till 37 degrees Celsius of the ambient temperature, and at 32 degree ambient temperature, it shows 7% higher efficiency compared to 404A. And for this parallel compression with ejector shows more efficient at all ambient condition, and it shows 10% improvement in the cycle efficiency compared to R404 at 32 degree temperature. Now these are the potential applications. So this is being built in Norway. These are the already installed CO2 system with this step. Now moving to the application of ejector in refrigeration system. So ejector, this slide shows that ejector has been utilized in all possible way in different refrigeration system or existing refrigeration system. So this I slightly explained in the previous earlier slide, where the ejector has been mechanical compression has been replaced with the ejector, ejector, generator, and the pump. The driving force we can utilize from the solar in the refrigeration system, ERS without a pump. So in these systems, we have a small pump that needs that has a moving part. So even we can remove this ERS, the refrigeration system, and we can work without a compressor. So there would be no moving part in complete system. In adsorption system and adsorption system also ejector has been utilized. Combined compression and ejector refrigeration system, the multi-component ejector refrigeration system, and transcritical ejector refrigeration system TERS. So in most of the refrigeration system, ejector has been utilized. So I'll just touch upon this simple ejector refrigeration system, solar powered, transcritical, and multi component ejector refrigeration system. People just can go through the review paper by Vaishak in 2016 for the more detail in these systems. So here is that simple refrigeration system, simple ejector refrigeration system, where ejector is replaced by the ejector has been used in place of the mechanical compressor, or ejector is used as a compression device. So the main principle of this system is that after condenser will try to pump the liquid to high pressure, and the power required for this pump is almost 10% than what we required for the mechanical compression to compress the vapor. So to now the high pressure liquid, we can provide the low grade energy or the waste heat energy to produce high pressure gas. That enters in the ejector as a primary fluid, and secondary fluid comes from evaporator. They extend the energy and momentum inside the ejector, and then reject heat to the condenser, and then split in two parts, one sent to pump and the one sent to evaporator through throttle valve, and this cycle completes. So in this system, the main source is that from where we can get the heat to produce high pressure gas, high pressure to produce high pressure vapor from the high pressure liquid. So people had tried utilizing the waste heat from the solar heat, and since solar heat available only in daytime, so we can use the storage tank also to provide continuous cooling. This heat also can be taken from the existing power cycle or the compression, the refrigeration system. So these are the utilization of waste heat to drive the refrigeration system. Here in this case, then we are utilizing the heat rejected from the another vapor compression cycle to drive the evaporator. In this this diagram, ejector used in the series. So the performance of these systems I'll explain in the following slide. The main issue using ejector is that control of the ejector or the variable load of the evaporator. So there is a slight issue in the ejectors. To avoid those ejector or to overcome this issue, people start using multiple ejector. So the mass flow rate of the primary and secondary get adjusted based on the evaporator load. In this system, we have the multiple evaporator that works at the different temperature level, and we had used two ejector to just recover the work, and that works fine. Now in the transcritical ejector refrigeration system, TERS. So this system is well explained in the previous slide, where ejector has been used as the expansion device that utilize the high pressure gas from the gas cooler to elevate pressure slightly coming from the evaporator. So it requires the lesser compressor work and improves the system efficiency. In addition, it also reduces the irreversibility of the system. And to recover more expansion work, people have even tried this 10 et al. Tried two different ejectors in the series. So first, a lot of work will be recovered from this ejector, and then it passes to the separator, and the gas comes in the second ejector as a primary flow, and secondary flow comes from the evaporator. So we can recover even more work. And these are the performance characteristics of the ejectors with the single performance curve of the system with the single ejector, basic cycle, and the two ejectors. So we can see with the two ejector, obviously system performance better than either single ejector or the no ejector. The similar to the transcritical system, we have even the optimal pressure, distillate pressure for these system as well. And here how the COP vary with the second evaporator, second ejector, as different the primary the primary ejector increment ratios. Now this slide shows that the use of internal heat exchanger along with in combination with the ejector. So we can see the efficiency of the system increases. This is the without heat exchanger, and if effectiveness of heat exchanger increases, the efficiency increases. This is the total exergy losses while using an ejector, and this graph is just optimization of the distillate pressure at different ambient conditions. So on this slide shows that the combined effect of ejector and heat exchanger. So we can see at lower condenser pressure, the heat exchangers are beneficial, but if we're using ejector as well as the heat exchanger after that, so it is not always beneficial. We can see the efficiency or the COP decreases at higher condenser pressure. So we need to just check whether we can utilize the heat exchangers while using ejector or not before just commercializing in these systems. As I mentioned that the component efficiency also affects the ejector performance as well as the system performance. So this slide shows that ejector performance or the system performance based on the different ejector efficiency. So here they have taken ejector 6 having the primary nozzle efficiency of 0.9, secondary nozzle of 0.9, mixing that area efficiency is 1, and diffuser is 0.8 as a reference. And then this Pujram et al has plotted the COP at different condition, different component efficiency of the ejectors, and we can see how this COP changes with slightly changing the efficiency of the nozzle. So we need to consider these efficiency accurately while designing the ejector. In this slide, ejector, this one Van et al has shown the effect of placement of the ejector. So he has the simple 2 evaporator system, and he has placed the ejector at different locations. So in the first size system, this is the basic that after this heat exchanger, they have put the ejector, and then we have 2 different evaporators. In the other case, this ejector has been used after the fast food evaporator. In this case, the coming from here, and the secondary flow coming from the freezer evaporator. Like that, they have given 5 combinations, 5 different configurations, and this shows this these configurations are provided better efficiency of 2.78. And now this is that 2-stage ejector I mentioned in the previous slide. So with this schematic, they have shown this 2-stage ejector performs better than single ejector or without any ejector. And these are the exergy losses of the 2 ejector and the single ejector. So that comes to the summary of this talk. So ejector are simple devices that utilizes pressure energy of high pressure stream to entrain and compress the low pressure stream. No moving part and simple construction of ejector led their ubiquitous application in many energy and aerospace domains. The critical mode operation of ejector results in the consistent performance, and that's why we prefer using the critical mode operation for the energy applications. The flow structure within the ejector operating in the critical and mixed mode region are completely different, as we see from the slide images. Ejectors are extremely studied in various existing systems to enhance the overall system performance. Augmenting TCO2 system with ejector reduces reversibility and power input to the compressor, increasing the system performance. Now I would like to acknowledge Professor Jagdish, Professor Pramod and Srisara, who helped me during the PhD work, and Professor Pramod Kumar is still continuing as my mentor in the postdoc. The LHSR member who helped me conducting the experiment, Binod Ladori, is with me now for the postdoc. Professor Armin Hafner, Dr. Heather and Simarpreet, who is mentoring my postdoc work, in line with the Dr. Hatton from Sintef. Professor Maya also helped a lot during my postdoc. In the postdoc teams, we generally speak internally to discuss several aspects, and Dr. Tondan Tunwar from Danfoss, India, for helping me understanding these systems. Now these are the references. Thank you. So I would like to take any question if anybody has.
Thank you, Dr. Pradeep, for the excellent presentation. If any of the participants have any question, please ask. I think no one has any question. So
hello.
Yeah.
Can you show me the diagram which has got two ejectors?
Yes, sir.
One is at the is, I didn't see the slide number.
Oh, I'll just show
Yeah,
this one.
this one. Yes,
Yes, sir.
How it works now? What is the high fund of this?
So this ejector works as a similar how this single ejector works, and then to just recover more expansion worth, the vapor of this the liquid of this suppression will send as a primary fluid. So this as a primary flow is a liquid, secondary is in vapor, and then it expand in the ejector, further expansion.
If you got only one ejector,
Yes,
what would happen? What is this? Why you want two ejector like this?
So in this case, we are recovering the expansion worth, as everyone we know that we have studied a lot. So still there are some part of the expansion worth is left in this system. So they try to utilize that the other part of the expansion was as well with the another ejector.
What is the pressure level? You got A evaporator and B evaporator, same pressure. Yeah, A gas cooler and B gas cooler, same pressure.
Yeah, gas cooler pressure is same, because this whatever this drop shows here, that is corresponding to similar paper. So
see, you are comparing A and B.
yes, sir.
Okay, that's two configurations for the same condition of gas cooler pressure, temperature,
Yes,
or
sir.
pressure or ambient temperature. And what is evaporator pressure? Also same.
It should be same. I am not very sure. I'll just go through. I think it should be same, because they are just changing this evaporator pressure, and they have plotted the COP of these two different configuration as well. So the evaporator pressure and the gas cooler pressure should be same for these two configuration.
So then why two ejector is more efficient than the single ejector? What makes it more ejector? Because
So,
the ultimately you want to recover the work from the high pressure gas. In the second case, initially your ejector works at the motive steam, or the motive gas steam doesn't expand to lower level. It's an intermediate level. Again, it is expanded in ejector for the lower pressure.
yes.
So I can understand two-stage compression with intercooling, some benefit, some theory is there. Here, can you explain what is the theory, or what is the concept behind two ejectors? Okay, for example, you got two compressors in series with intercooling.
Yes.
If there is no intercooling, there is no use.
Yes.
Okay, you may use two compressors, because one compressor will not be able to take up that much of pressure ratio.
Yes.
So there's a reason for using two compressors in series with or without intercooler.
Intercooler, yes, sir.
So from that, like that, can you explain the use of two ejectors in maybe in like something in series? Otherwise, we don't know. You are telling something and we can't understand why. Hope you understood my question.
Yes, sir, I understood the question. The paper, what I get from this paper, they are saying this using single ejector, they are utilizing the pressure worth or this pressure energy from the gas cooler, and still some part of the energy expansion losses are there in this system. So to recover that expansion losses, they are using the second ejector, where they are using this liquid from the separator sending as a primary fluid, and the evaporator they are sending a secondary to recover some part of the expansion worth or some expansion losses what we authored after the separator.
See, hello. The
Yes.
First ejector is not recovering full because you are not allowed it, because it is not coming to the down pressure. You are operating at higher pressure. That is why it is not recovering. See, you are constructing, you are restricting it from recovering full. See, that is why if you put pressures of gas cooler pressure, evaporator pressure, ejector, inlet, outlet, all these things, then it will be clear. Because you are in the second case, what I understand, that you are not allowing the ejector to recover all the things. You are making it to not recover. Then you are saying that it's not recovering, then you are getting one more ejector. I may be wrong. I'm not telling that what I'm doing, but I am not able to comprehend the reason why you are using two ejectors. That's all.
I'll just go through this paper again and I'll try to answer your question.
Okay.
As of now, I had that.
Okay. And again, you are see in this two throttle valves are given.
Yes, so that throttle valve for control issues, sir. So
One
in
is
this,
liquid, one is vapor.
no, this here, yeah, this is vapor. So sometime ejector increment ratio clashes with this the dryness fraction at the end of the separator. To just resolve that issue, we have provided this two throttle valves here.
So partly it is compressed, partly it is throttled.
Here, just for the control issue, so maybe 5% or 10% those compressor and some in the throttle. So we cannot say exactly how much it would be, but it's very low number, because the increment ratio of this ejector and the dryness fraction of dryness fraction at this end of the separator has a relation. So to control that relation, we had provided one extra throttle valve here. So with this, I think I can explain in better way. So it's simple. So here, if you see this, let's suppose the dryness fraction at the separator is H. So if let's suppose there is no throttle valve at this throttle valve, so this H goes here, and that comes as a primary flow. Another is if this is 1 minus H, and the increment ratio would be H divided by 1 minus H. So to control, sometimes this relation does not very true because of this ejector increment ratio. To provide the consistent or there is no mass accommodation, we have provided this two throttle valve.
But in that case, the vapor that is getting throttled,
yes,
slightly, it is getting compressed again in the ejector. That part. Let's say throttling valve 1, 2. One is liquid. Fine.
Yes, yes, sir.
Other is vapor, right?
Yeah, this other is vapor.
Yeah. That is you are throttling it, and again you are using the same ejector to compress it. Again throttling it, again compressing it. That is useless. No, it's lost. No.
No, this compress again, sir. Actually, if I can write something, so there is a relation between the increment ratio is equal to 1 divided by 1 minus H. So it's always not true because of we cannot control ejector increment ratio very accurately. To just balance that equation, ER is equal to 1 divided by 1 minus H, we had provided this throttle valve. So the mass flow rate here may or may not come. If the equation satisfied, this throttle valve or the throttle valve which has the vapor may not even open anything. Otherwise, it opens only for 5% or even lesser than that, just to control the mass balance in the ejector. So it's not like that half or maybe it's 80% of the vapor comes to the throttle valve and those to evaporator are there. It's not like that. It's just about less than 5% or so, or even lesser.
Is it not better to control the compressor so that everything is compressed? See, now what happens is your energy you are using in the ejector, the energy of the expanding gas you are using the ejector. Right?
Yes.
After the gas cooler, you are using that energy to compress.
Yes, sir.
Okay. So now that energy is used to compress the liquid that is throttled is perfectly all right. You are using that energy also to compress little bit of vapor that is throttled.
Yes.
That is useless. So it's better to control the compressor such that the second throttling is always 0.
Okay.
Depending upon the ejector capacity that compressor is taking.
Yes.
If ejector is requiring less, then it compresses more.
Let's suppose, sir, slightly change in the increment ratio here, and that the complete vapor is the primary flow is coming from the compressor itself.
No, sir.
So,
if see now ejector can compress 10 units.
Yes,
okay,
sir.
But my liquid is only 9 units.
Okay.
What happens? It will work. No, ejector will work. Why should you give unnecessary junk to it? Just because it can see lorry is going with the 3/4. Okay, and you say that it should be fully loaded, you put some more, only to be brought back.
Okay.
What do you use? Let it go 3/4. What is the problem?
Sir, if this secondary mass flow rate is lower, then ejector may not choke inside the secondary flow may not choke inside the ejector, sir. So we need to have the secondary mass flow rate, what it required, and or what we can calculate from the intermittent.
It cannot be less than the something design one. It cannot be less than design one.
If it's less than design one, or the secondary flow is less than design one, then secondary flow does not choke, because we have to have the secondary mass flow rate to the choking mass flow rate, or equal to the choking mass flow rate. If it's less than secondary flow may not choke, then ejector operates in the mixed mode operation instead of the trickle mode operation. So that's the issue, and
that means the lorry should go always full load.
The secondary
cannot
flow,
go 3/4 load.
So secondary flow should be that whatever the design condition is. Otherwise, we need to use maybe a different whatever we can use different ejectors. If you are using single ejector, in that case, the secondary flow has to the critical mass flow rate. Otherwise, it operates in the mixed mode operation.
Okay.
And to just avoid this issue, people start using multi ejector system. So one of the other ejector will be choked, and will use that particular ejector in change depend upon the ejector load, evaporator load.
Okay. Thank you, Gupta. Very nice presentation. Thank you very much. Thank you.
Thank you, sir.
Thank you.
Someone
Next
has
question, please.
I can see.
Hello.
Can you hear me?
Not very clear, but yeah, I speak. I think your voice is breathing.
So I just had a simple question. Is there a theoretical maximum limit for the entrainment ratio possible for a given nozzle geometry and for a given motive pressure?
The theoretical limit, so that depend upon this thing. There's no limit. It can even the intermittent ratio can go even beyond 1, and we had achieved that beyond 1 for the critical mode operation. So whatever result I have shown here, we can see clearly 0.7 or so for few cases.
So
here
you are saying that there is mainly for balancing loads, especially for applications where we want to use both the heating and cooling effects. So the motive flow is also part of the design, and the suction flow also affects evaporator load. Is
yes.
there an basically, can we tailor the operating conditions to have any combination of primary and secondary flow for a given motive pressure and for a given boost?
The differently, actually, most of the things I have explained here in terms of the intermittent ratio and the non-dimensional number. So, and we have not checked for the secondary flow variation, because almost all the time ejector is the secondary flow is from atmosphere. But in terms of the SPR value, we can see even we change this SPR slightly, ejector operates in the mixed mode, critical mode operation, and the intermittent ratio changes accordingly to that. So slight change in the ambient and slight change in the pressure values or motive and the secondary flow pressure, ejector still operates in the this critical or the design operation by changing the intermittent ratio and the critical compression ratio based on the operating condition. So it may or may not operate in the design condition. If we outside the dome, we just whatever we have plotted here for this pressure ratio. So we are changing the pressure ratio in this case. So if we are in this region, or the compression ratio is from 1.2 to 1.45 for this particular case, ejector operates in the critical mode operation. If the compression ratio goes beyond, ejector start operating in off design condition. So this similarly for different SPR or NSPR here means the ratio, the primary flow stagnation pressure to the secondary flow stagnation pressure. So these envelope we need to consider while designing the ejector. So we have to operate ejector below this critical pressure for ensuring the on-design condition of the ejector.
Okay, thank you.
Participant have any questions? Okay, if no one has any questions, let's move on to today's second session. In this session, we have two speakers, Dr. Siva Reddy and Dr. Vaishak S. The first part of this session presentation on CO2 heat pump chiller for hotel application will be presented by Dr. Siva Reddy. So now I will introduce Dr. Siva Reddy. He is currently postdoctorate fellow at Indian Institute of Technology, Madras, working on the Indo-Norwegian project Indy Plus. Dr. Siva has carried out research on liquid descent air conditioning system for air conditioning application as part of his PhD course. He has received PhD and MTech degree from National Institute of Technology, Warangal. Before his PhD, he worked as an HVAC engineer in Chennai for 3 years, where he worked on designing ventilation and air conditioning system for various buildings in a thermal power plant. Currently, he is working with an Indy Plus team to model, develop, and install a CO2 heat pump chiller unit at a hotel in Chennai. So I request Dr. Siva Reddy to proceed with the presentation on CO2 heat pump chiller for heat application, for hotel application.
Thank you, Vinod. Is my screen visible?
Yes, it's visible.
Okay. Thank you. So thank you, Vinod. So good evening, all the participants.
Dr. Siva, can you make this presentation mode?
Wait. No, Vinod.
No.
Not. Now is also same, not changed.
No, okay.
Now is okay.
Okay. Thank you, Vinod. So good evening to the participants and the panel members. So today I'm going to deliver a talk on CO2 heat pump chiller application for hotel. So how the CO2, that is energy saving potential of CO2 heat pump chiller, as well as how much it can reduce the emissions from a hotel. So I'm going to deliver today. So before going to the topic, first I want to share the how much buildings are contributing for energy consumption as well as emissions. So if we see, almost 35% of the energy is being consumed by the building sector, and nearly 38% of the emissions are being contributed by building sector. And in building sector, if we consider the hotel sector, nearly half of the energy share is being consumed by space cooling or space heating, and 13% for hot water. So these are the energy shares of a hotel sector. So if we see these shares, there is it is a essential need to focus on building sector to mitigate the emissions as well as to reduce the energy consumption. So there is an need to look on energy efficient solutions. So in our today I'm going to discuss on how a heat pump, CO2 heat pump, can reduce the emissions as well as how much it can save the energy consumption for hotel. We'll see. So for hot water generation, normally in India, fossil fuel fired boilers are being used to generate the hot water, which are not only environment friendly but also will liberate high emissions. So there is an essential need to need for efficient solution for hot water generation in hotel sector. So one of the solution is heat pumps. So as we know, heat pumps are it will transfer heat from one zone to other zone by taking work input. So compared to conventional heat sources as like fuel-fired boilers are, they will just generate the heat. But if you see the heat pumps, they will transfer heat from one zone to other zone with the work input. So it will generate heat several times. It will generate the energy several times than the energy input. So that's why heat pumps will be very efficient solutions for heating applications. So in these heat pumps, there are so many refrigerants are being used, out of which already CFCs or HFCs are being phased out, and HFCs are also being phased down. And what we are left with are natural refrigerants and hydrocarbons. In natural refrigerants, CO2 is the excellent refrigerant, which is a safe, non-flammable, non-toxic, very cheap refrigerant with excellent thermal properties, and which is having negligible. That means global warming potential is 1, which makes it is a prominent refrigerant of choice. And in addition to that, using CO2 in refrigeration systems can be considered as an alternative form of carbon capture also. So like from many industries also, we can easily capture without dumping into atmosphere. We can capture the CO2 and which can be used in refrigeration system. In that way, we can help to relieve the effect on climate change also. So a CO2 heat pump integrated with thermal storage tank is proven to be very energy efficient and environmental friendly solutions compared to conventional existing sources for simultaneous cooling and domestic hot water production. So this is the potential of CO2 heat pump applications. And in India, the adopting of CO2 technology is in slow pace because of lack of awareness and lack of local expertise and lack of awareness of energy saving potential for in these type of applications. So our project team, Indie Plus project team, aims to install a demo sites like CO2 demo sites in specific applications like hotel or some in hospitals, which will demonstrate the technology, and with which we can show how much energy savings we can attain and how much will be the payback period. So all this can be possible with the demo site. So with this intention, we have visited a Holiday Inn hotel in Chennai. This is the Holiday Inn. So we have visited this hotel and we have surveyed what are the hot water requirements and what is the source they are using for generating this hot water, and what is the hot water pattern. That means what is the peak time period, and what are the various applications in hotel for hot water. So all these are being surveyed. So if you see from this, normally this is Holiday Inn hotel is having around 200 rooms. So for this hotel, the rooms requirement is around 30 KL, whereas for kitchen and other public washing areas, it is around 8,000 liters. So total is around 38,000 liters is the hot water requirement. So normal ambient temperature, normal water temperature is around 30 degrees we are considered. So hot water temperature is near to is around 48 degrees. So we need to heat with delta T of 18 degrees. So with this data, the heat requirement per day becomes 2,385 megajoules per day, and there will be some circulation losses. So with consider this is the hot water heating requirement, and for serving this hot water, they are using 2 hot water tanks, one for rooms and one for kitchen. And this is the fuel they are using, high-speed diesel. And daily to serve this heat, they are using nearly 115 liters of diesel. So with this fuel price, almost day-wise, nearly they are spending 11,000 rupees, and annually they are spending around 37 lakhs of rupees on diesel only to serve the hot water demands. In addition to this, these are the emissions which are being released from the diesel. So, and also these are the hot water discharge pattern. So normally in the morning hours and in the evening hours, more hot water will being consumed. So in the from 6 to 9, as well as in the evening 8 to 10. So these are the peak times. And so this is the existing hot water system they are using in their hotel. So I will just explain. So these are the 2 hot water tanks they are being used. One for supplying hot water to rooms, one for supplying hot water to kitchen. And they are using diesel-fired hot water generators of 232 kilowatts rated capacity. One is standby. So they are supplying the hot water, so which will be continuously circulating, and there is a plate type heat exchanger is being used. And these are the mixing tanks also. So whenever the temperature drops than the requirement, like 46 or 45, then it will gain heat from this plate heat exchanger, and in this way this hot water tank will be always maintained at 48 degrees, and this will be supplied to rooms. And if not used in the rooms, it will be recirculated. That means it will again come back to the tanks through this hot water return lines. And to supply to balance the pressure, these are the pressurized tanks, this 7 bar and 4.5 bar. So whenever hot water being is used, then automatically this pressure will be dropped in these tanks. To balance this pressure, water will be supplied from the pneumatic system to balance the pressure. So in this way, it will balance the pressure, and this hot water generator maintains the temperature. So this is the existing hot water system in the hotel. So now I will show how we are proposing our CO2 heat pump chiller is being integrated in this system. So first, so this is we are tapping cold water from the pneumatic system, and we are supplying this cold water to CO2 heat pump, where it is being heated to nearly 70 degrees in the gas cooler. That hot water will be supplied to thermal storage tank. So we are supplying hot water at 70 degrees to thermal storage tank, and whatever we are getting chilled water as complementary, that will be connected to the existing chilled water system, so that we can save the existing chiller load. In present, their chilled water chiller is around 340 TR. So we can save nearly 3 to 4% of their chiller load with our CO2 heat pump by serving the hot water demands. So after being stored in the thermal storage tank, this hot water will be supplied to the hot water tanks after being mixed with the cold water. So that these temperatures will be maintained always at 48 degrees. So 70 degrees of water will being tapped from the thermal storage tank, and 30 degrees water from pneumatic system will be mixed here, and after mixing it will become 48 degrees. So there is a temperature sensor which will control this valve, so that always this temperature will be around 48 degrees. So in this way we are supplying 48 degrees water using CO2 heat pump and thermal storage tank. And as I told, there will be circulation losses in the hot water return. So to compensate this circulation losses, we are proposing a recovery heat exchanger. So there is a recovery heat exchanger. So this is always at 70 degrees. And so whatever the water coming from the return line, which will be supplied to the heat recovery exchanger, so where it gains the heat from this thermal storage tank, so that this water also will be always at 48 degrees. So in this way, we are supplying 48 degrees a constant 48 degrees water to hot water storage tanks. So this is the integration of CO2 heat pump system with thermal storage tank, which we have proposed to total. And now we have to size this, how much capacity is required for CO2 heat pump and what is the size of this thermal storage tank. We need to size it. So we know the hot water demands. So we know the hot water patterns. So these are the hot water patterns. So as I explained earlier, so this is the peak demand. So in these 3 hours, almost 18 KL of water will be consumed by the rooms. So if you see this second graph, this is the consumption rate and this is the availability of hot water. So when we are employing around 50 kilowatts of heat pump with 6 KL thermal storage tank, so always there will be enough hot water available, but at peak time, it is exactly matches. This is the peak time around 9 o'clock. So this will exactly match the requirements. So this heat pump capacity and thermal storage capacities are perfectly suited for these applications. When we go to 40 kilowatts or 30 kilowatts, we cannot supply the hot water requirements in peak demand. If we can go to 60 kilowatts also, but we can get the hot water demands, but it will induce us the additional investment cost. So this is the optimum size of heat pump as well as thermal storage tank, which will exactly suits the requirements. So this is how we can match, and this is the heat pump control strategy. So normally this is the peak time. So whenever hot water is being consumed, then automatically heat pump will switch on and it will continuously supply the hot water to thermal storage tank. So it will continuously runs because even it is supplying to thermal storage tank because of hot water demands. There will be a drop in the level in the thermal storage tank. So to maintain that level, so it has to run continuously up to this time. And in the night peak times also, it will continuously run until the thermal storage tank gets filled 100%. So in this way, heat pump will control based on this hot water requirements. So this is the heat pump configuration we are considering. So there is a single evaporator and with ejector, IHX, and one gas cooler and single compressor. So this is the heat pump configuration we are considering. So whatever the we are tapping the chilled water from the existing chilled water loop, and we are supplying this water to the evaporator, where it being cooled to 7 degrees from 12 degrees, and again it will be supplied to the chilled water supply header. So in the gas cooler, we are tapping the cold water from the pneumatic system at 30 degrees, where it will get heated to 70 degrees, and there is a thermal temperature control valve which will controls the water flow rate to get the 70 degrees water. So after getting heated, this will be stored in the thermal storage tank of 6 meter cube tank. And there is a level switch also included in the tank. So whenever it drops to some 95 degrees, this level switch will actuate the compressor so that heat pump will starts working and it will supply the hot water. So whenever it gets 100%, it will get it actuates the compressor and it will get switched off. So in this way, this level switch actuates the compressor. After being stored this hot water from thermal storage tank, and this will be supplied to hot water storage tanks. after mixing with the cold water. And as I explained, this is the heat recovery heat exchanger. So this is how we are controlling this heat pump as well as this pump to serve the hot water demands for hotel. And this is the hot water pump control. So based on this hot water discharge pattern, this pump also is being controlled. So whenever the rooms requires hot waters, then automatically this pump will switch on. This pump one is this one. So whenever any guest or anyone is consuming hot water, there will be drop in this pressure. So at the time, this P1 will actuates and it will supplies the hot water to the tank one. So in this way, P1 is being controlled. So this is the peak time. At that time, P1 also will work according to these times. P1 is also starts working. So this is the control strategy for P1. And with this configuration, we can see how much cost savings we can attain and how much emissions can be reduced. So if you see these figures, so CO2 heat pump system cost per day. So this is the 15 kilowatts is the energy consumed by the CO2 heat pump, so which includes power consumed by the compressor, power consumed by the pumps. So it has to meet the demands, heat pump has to run nearly 18 hours. So at the electricity price of 9 rupees per unit, daily operating cost will becomes around 2,400 rupees. And additionally, we are getting 37 kilowatts of cooling as chilling benefit. So at 0.85 kilowatt per TR, this is the chilling benefit we are getting. So because we are supplying this 37 kilowatts of cooling, this same load can be reduced in the existing chilled water loop.
What you want,
so that means this amount is this amount we are saving per day. So net power for heating is 6.1 kilowatts. That means 15 kilowatts. And for chilling benefit, we are with chilling benefit we are saving 9 kilowatts of chilling. So net power is around 6 kilowatts. So net cost for hot water per day, it becomes 970 rupees, and annually nearly 3,40,000 is the operating cost of this CO2 heat pump system. On the other hand, if you see diesel consumption and their operating cost, with 150 liters of daily consumption, 10,800 is the operating cost per day, and annual cost is around 37 lakhs. If we can see these two figures, we can see huge savings can be achieved with the CO2 heat pump chiller. So almost 90% of the savings can be attained with the CO2 heat pump chiller. So total operate cost savings is around 9,900 we can attain, and annually 34 lakhs is can be attained as the cost savings. In addition to that, emissions also can be reduced drastically. That is 70% of the emissions also can be reduced with the proposed system. And also a return on investment is found to be less than 2 years. And these are the graphs which will show annual operating cost savings and CO2 emissions reductions. If you see these graphs, this is nearly 37 lakhs they are spending to generate the hot water by using diesel. So by installing CO2 heat pump, only 3.5 lakhs is enough to operate. 3.5 lakhs is enough to serve the hot water demands. So if you see CO2 emissions also, these are the emissions we can reduce. Nearly 70% of the emissions can be reduced per year. So this is the energy saving potential and emissions reductions possible with the proposed system. So we can see conclusions. hotels, as I told, these are energy intensive building which require simultaneous cooling and heating. For cooling, the chillers are being used, but for heating, in India, normally all hotels are using conventional heat sources as natural gas as or diesel are being used to generate the hot water. So these are not only energy efficient, but also release huge emissions. Heat CO2 heat pump integrated with thermal storage tank is globally proved to be energy efficient and eco-friendly and alternative for domestic hot water demands. And this system also complements to nearly 3.2% of the total cooling demand of the hotel by providing chilled water at 7 degrees. So these are the savings and emissions reductions. 90% and 70% can be attained with the proposed system. So as I told, ROI is found to be less than 2 years. So this is the energy saving potential of CO2 heat pump chiller for hotels. Not only for these hotels, wherever simultaneous heating and cooling required, like dairies and hospitals and hotels and spas. So wherever these are required, this is the one of the best eco-friendly solution we can adopt. So this is my presentation. So thank you. Any questions? Please.
Thank you, Dr. Vaishak Reddy, for the excellent presentation. I request participant to keep your question for after second speaker. Now I would like to introduce second speaker of this session, Dr. Vaishak S. He will present on CO2 for dairy application. Dr. Vaishak S. is an ND Plus postdoctoral fellow at Birla Institute of Technology and Science, Pilani. Dr. Vaishak has carried out research on the integration of photovoltaic thermal systems with heat pumps to develop more energy efficient technologies. He received his PhD in 2021 from the Sardar Vallabhbhai National Institute of Technology, Surat. After earning an MTech from the same institute, his main area is expertise includes CO2 refrigeration systems, photovoltaic thermal systems, biofuel, etc. Currently, he is working with the ND Plus team to develop and implement CO2 ammonia cascade and transcritical CO2 refrigeration system in India. So I request Dr. Vaishak S to proceed the second part of this presentation.
Okay, thank you. Is my screen visible?
Yeah, screen is visible.
Okay, full screen.
Yeah, visible.
So my topic is I'm talking on how we can use this CO2 for dairy application. So related to the same topic, there was one previous presentation where how CO2 can be used for simultaneous cooling and pasteurization. So we are extending that and we are explaining few more applications in dairy industry. We are highlighting what are the temperature requirements for cooling and for heating. So if you see dairy, it is an important part of the global food chain. And if you see the worldwide production, India stands first among all countries with an annual production of approximately 210 million tons. This is the statistics in the last year, that is 2020-21. And in order to deliver this product to the milk to the end user at its best quality, the refrigeration plays an important role in its complete supply chain. In addition to this refrigeration system, there is enormous heating requirement for various processes like pasteurization, other manufacturing processes which is involved in this processing of this milk, then cleaning and sterilization, etc. So first we will see how this supply chain in this dairy industry happens. So this is an approximate schematic of the supply chain in the dairy industry. So from farmers, the milk will come to a collection center. Either they will deliver the milk by themselves or through a collection agent. So in the collection center, the milk is stored in a container where it is being chilled to a lower temperature than at the temperature which is being received. And this collection center, it is having a milk cooling or milk chilling device, which is specifically known as bulk milk cooler.
Dr. Vaishak, you are not audible. Sorry.
Okay. Am I audible right now?
Audible only.
Okay.
Okay now.
Okay. So this bulk milk cooler or bulk milk chiller, that is commonly known as BMC. From this bulk milk cooler or the collection center, this milk is being transported to the processing plant through refrigerated trucks. And in the processing plant, it undergoes a series of operations where different products are being produced, and from there it is being delivered to the customer. So the refrigeration requirement and the heating requirement generally starts from the collection center or the bulk milk coolers. Generally, when we extract this milk, it is at a temperature of 35 to 37 degrees Celsius, and it has to be chilled to 4 degrees Celsius to check or to reduce the growth of bacteria, which will reduce the quality of this milk. So the image which you see is a photograph of a BMC.
Vaishak, there is disturbance.
Yes, sir.
There is disturbance at your end.
The voice is breaking, or
No, some other sound is coming.
okay, actually background it is okay. I will check with this. Okay, so the this is the bulk milk chiller, and this is the pouring tank. We pour the milk into this pouring tank, and using a pump which is located at the bottom, it is being pumped into the chiller unit where it is being cooled. This same pump is used to transport or pump this milk to the collection tankers also, where through which it will be transported to the processing plant. Generally, this pull down time of these chillers, it varies from 4 to 6 hours, and it depends upon the capacity of that chiller unit. So this refrigeration means for this application at collection centers, the refrigeration systems generally used are based on either on R134A or R404A or 407C or R22. The older units are generally based on R22. At this stage, for this application, we generally don't use ammonia. Ammonia is basically for large size dairy application, or where the processing take places. So once this milk is being pumped to the this collection means transporting trucks, all the components in the collection center has to be cleaned, and this is a very important process in this supply chain, because the next batch when we are loading, it should not get spoiled with the bacteria or the remainings of the previous processing batch. So this cleaning, it can happen either means it can take place through manual process or through clean in place process. In the coming slide, we will be looking in detail what is this cleaning place process and what are the temperatures which are involved in this process. So for this heating application or for this cleaning place application, we are requiring generally up to temperatures of about 80 to 90 degrees Celsius water. For for producing that temperature water, we sometimes use heat recovery from the cooling unit to heat the water, preheat the water, and it will be heated to the required further it will be heated to the required temperature through the backup heaters, or we will directly use electric heater for this application, or instant gas heaters are also being used, and in some cases solar water heaters are also being with backup electric heaters are also being used for this particular application. So coming to this dairy processing application, here dairy processing plant. So when the refrigerated trucks which carries the milk reaches the processing plant, a quality check is done initially, and once the quality check is the trucks, the milk in the trucks pass that quality check, the milk is being pumped to the silos. Silos means they are large cylindrical tanks where these milks are being stored at a temperature of 4 degrees Celsius. So from there, the processing of this milk start. So from there, either if we don't want to separate the milk means if you don't want to separate the fat content in that, then the complete milk, which is specified as whole milk, it will move to the pasteurization unit where it is being heated to approximately 72.5 degrees Celsius and kept at that temperature for 15 seconds, and it is being again be cooled to 4 degrees Celsius. So this is the one of the temperatures at which the pasteurization is being done. The temperature may vary, then accordingly the time for which that heating process is being carried out also varies. So if the whole milk is the processing, whole milk is pasteurized, then it is passed through the homogenizer where we reduce the size of this fat molecules, and it is this homogenized milk is then passed to the milk packing or transported to the milk packing unit where it is being packed in containers, and if before dispatching from the processing plant, they are stored in the cold storages where which are generally kept at temperatures below 5 degrees centigrade. So in some cases or in some for some other application, this whole milk is passed through a separator, which is usually a centrifuge, where we separate the cream and where we separate the cream from the whole milk. And these two parts, that the cream is being transported for the or passed for the production of butter, ghee, and all those kind of products, and the skimmed milk, which is having very low fat content, it is being passed into the for the production of our milk powder. Please note here, we can also use whole milk also for milk powder production. That depends upon the that processing plant. Now this skimmed milk for milk powder production, the skimmed milk is first condensed means in that the water in that skimmed milk is being evaporated at a temperature of 80 to 85 to 90 degrees Celsius so that the water content in that milk will get reduced, and this condensed milk is then dried using hot air at a temperature of 180 to 200 degree centigrade. And this after this drying process, we are obtaining the milk powder, and this happens in a spray drying system is there for producing this milk, for converting this skimmed milk into milk powder. And the other circuit, that is the cream. From cream, generally in the processing plant, the butter is being produced, and from butter, the ghee is being produced. So if you look at that process, a heating up to 120 degrees Celsius is required, which is generally at the ghee boiler, and a cooling for butter and all, the cooling or the low temperature which is required is 10 degrees Celsius. So this is a general layout of a dairy processing plant. In addition to the process which I have mentioned here, there can be other process also. For example, there can be curd manufacturing, which requires a higher temperature of approximately 90 degrees centigrade and a lower temperature of less than 5 degrees centigrade. And another process which happened in the dairy is the ultra high temperature process. This ultra high temperature process is generally applied to the product which is stored at normal condition. That means the product which is subjected to this ultra high temperature does not require refrigeration while storing, and it is having high shelf life also. A typical example is the milk which we buy in our Tetra packs. The Tetra packs are generally stored outside the refrigerator only, which does not require any refrigeration until it is being opened. So the heating requirement for those kind of process is approximately 135 degrees Celsius to 140 degrees Celsius. And this is also can be considered as a pasteurization or a sterilization process. at this temperature of heating, the process is being carried out only for 3 to 4 seconds, and it is being immediately cooled down to our normal atmospheric temperature, that is approximately 30 degrees centigrade. So that is another heating requirement which is required at this dairy plant. And sometimes there is a requirement of very low temperature cold storages also. A typical example is the butter which is being produced. If we want to improve the storage or the shelf life of that butter, it has to be stored at a temperature of minus 18 degrees centigrade. So there will be a cold storage requirement of minus 18 degrees centigrade also in dairy application. And in addition to this butter, if ice cream production is also there, it is also requiring a temperature of minus 18 to minus 20 degrees centigrade. Now, after the batch of this production, after one batch of production, all the equipments in that production line has to be cleaned and sanitized. There is a standard specification which is given by the Food Safety and Standard Authority of India. This is the minimum specification. It can vary according to the processing industry also. So it involves the initial rinsing with the warm water, then washing with an alkaline solution, then again rinsing with a warm water, then washing with an acid solution, then again washing or the final cleaning with cold water for about 8 minutes. And this is the minimum temperature. In some cases, according to the type of the detergent or the type of the acid and the alkaline solution used, the temperature can vary, and it can go up to 90 degrees centigrade also. And this is the general cleaning place strategy which is being followed. And on the right side, you can see the storage tanks for storing these solutions and all. And these solutions are pumped or sprayed to all the components which comes in the production line care. And this cleaning place, the cleaning process generally in the case of this dairy industry, it is we don't detach any of the pipelines or any other components. Generally, we keep at that particular or all the components are connected only. That by the time it is clean in place. But at the cooling center, the process can be clean out of place also. That means we will remove certain component and it will be taken to another point for cleaning application. So when coming to this large dairy processing plant, the most common refrigerant which is being used is the ammonia. However, we can see the application of R134 and some older units are using R22 also for their refrigeration application. And coming to the heating system, generally the heating requirement of that dairy industry is being met by the boiler with heat recovery systems. And in as a this step for promoting this renewable energy, now many industries are adopting a solar thermal systems also. In addition to that, there are other heat recovery units also in the are being used in the dairy industry. One is the common heat recovery unit from the cooling unit. And if there in the dairy industry there are large air compressors also, heat recovery from the air compressors are also being practiced in the dairy. The photograph which you see here, this trough field, this corresponds to the an Amul industry in means Gujarat, and which is being which is used to produce steam for their this processing applications. So coming to the type of CO2 systems which is applicable for this dairy application. For this normal collection centers and mini dairy plants, the CO2 system can be a single evaporator CO2 system. That means we are having a milk chiller which will chill the milk, and we are having a heating unit which is used to produce either hot water, or it can be used to produce or it can be used to support the pasteurization process. So this is a CO2 configuration which is applicable with this single evaporator configuration only. And this configuration we have developed with the ejector model, which is available with the Danfoss, that is the low pressure lift ejector. And this in this low pressure lift ejectors, these systems are not means it works with a very basic configuration than the high pressure lift ejector configuration. I will just come to the high pressure lift ejector configuration also. This one is the first image which I am showing. It is with a single evaporator, and the second one is with a dual or multi evaporator. So for example, if the plant requires a milk chilling as well as a cold storage of which is kept at -20°C, then that can be met by a multi evaporator CO2 refrigeration system. So the MD evaporator in this image, it corresponds to the application or the process of milk chilling, and the LT evaporator here, it corresponds to the application of cold storage, that is at -20. So if you see in this diagram, when we are using a low pressure lift ejector, all the refrigerant which is passing through the empty evaporator, it will be taken by this low pressure lift ejector, and it will that will lift the pressure of the refrigerant from this empty evaporator level to an intermediate receiver level. However, no refrigerant which is passing through the LT evaporator won't be taken by this low pressure lift ejector, because the pressure at this LT evaporator, it is outside the suction envelope of these ejectors. They have to be directly compressed from the LT compressed by the LT compressor, and it will be taken by the MD compressor through an intermediate D superheater. So in order to just see or just to show the how the mass flow rate it happens in this kind of system, I have taken two conditions. That means the operation of this system in summer condition and the operation of this kind of CO2 refrigeration systems in winter condition. So in the case of this summer operation, for example, if you see here, the ejector will be working in perfect condition. That means the ejector is capable of taking all the refrigerant from this empty evaporator and rising it to a temperature of rising it to an intermediate pressure, from which it will be taken by the empty compressor. However, when it comes to winter operation, the ejector won't be able to provide any lift there, so the ejector won't be taking any refrigerant from the MD evaporator. All will be taken by the normal application, that is all the refrigerant from the MD evaporator will be directly taken by the MD compressor fan. Now this system has the capability to switch between these two operations through this flash gas bypass valve here. That means when it is working in this ejector mode, we can call it as an ejector mode. This flash gas bypass valve will be 100% open, and it will be taking the 100% open, and it won't be taking part in the control of this intermediate receiver, pressure of this intermediate receiver. However, when the system works in the standard mode, that means the ejector won't be lifting any refrigerant from this MD evaporator. This flash gas bypass valve will be operational, and it will be controlling the pressure of this intermediate receiver. So if you see the numbers here, we can see that when it is working in the low pressure, means when it is working in the ejector mode, about 88% of the complete mass flow rate in the system is being from this intermediate pressure level. However, when it is working in the standard mode, that means just as a back pressure valve mode, then only 13% of the complete mass flow rate in the system is happening from the intermediate receiver. So here it is clear that how much amount of work we can save by using this ejector. Now, in addition to that low pressure lift configuration, it is possible to have a high pressure ejector configuration also. So the basic difference between the low pressure lift configuration and the high pressure lift configuration lies here. If you see the last image, there is no parallel compression bank or parallel compressor here. Only the main compressor, that is the main MD compressor, is available in the system configuration. However, when it comes to the high pressure lift mode, high pressure lift ejector configuration, we are having a parallel compressor to take the refrigerants from the intermediate receiver, and we are having the main compressor bank separated. So these high pressure lift ejectors, they are operational only with the parallel compression system. They cannot be made operational with the booster systems there. That is basically the limitation that their product range is having the Danfoss product range is having that limitation there. So in the this is just for the same condition. That means for an MT evaporator at 0 degrees Celsius and for an LT evaporator at minus 25 degrees Celsius, what is the mass flow rate happening through the different system we can see here. But in if you see here, when compared to the previous configuration, in the previous configuration, all the mass flow rate through the MT evaporator was taken by the high pressure lift ejector, but a low pressure lift ejector. But in the case of this high pressure lift ejector, only a portion is being raised to the intermediate pressure. The rest is being taken directly by the MT compressor here. But in the case of high pressure lift ejector, as the name suggests, it can be lifted to a very high, means approximately, if you see the values, up to 10 bar from the MT evaporator we can lift. But in the case of this low pressure lift ejector, that lift will be 6 to 7 bars. So I have just made a comparison here to have an idea how much is the COP. This COP mentioned is a cooling COP only, and what is the heating potential here. Here we can see the cooling COP of the high pressure lift ejector is high when compared to the low pressure ejector. But it has to be kept in mind that the high pressure lift ejector have a requirement of additional compressors and all, so it may increase the payback period and all. Please note here the loads which are mentioned here is very small, but this is just for a comparison purpose only. In actual cooling dairy processing plant, the load will be very substantially very high. So I'm summarizing the presentation here. So the use of natural refrigerant is very much essential for the phase down of these HFCs, and in that CO2 is a good potential refrigerant for an alternative. And this CO2 find a very good application in dairy because it can meet both heating and cooling requirement. So we are working towards an efficient and clean cooling technology. Before ending, I want to acknowledge the SPARC workshop organizer for giving me an opportunity for present, and our Indeed team, that is our head of our project, that is Professor Armin Hafner, and our entire team, which includes all the PAs, PhD students and postdocs, and our funding agency, that is the Norwegian Ministry of Foreign Affairs. I want to especially thank our professors Das Gupta sir and Bhattacharya sir, and also our PhD scholar that is present. So thank you for your attention and any questions.
Thank you, Dr. Vaishak for the excellent presentation. If any of the participants have any questions, please ask. Dr. Kamal Jyoti, ask together. Kumar and Vaishak.
Hello, am I audible?
Yes, you are audible.
Yes, you are.
Sir, in dairy plant, the milk is heated to 135 to above 100 degrees centigrade, and it is kept for 3-4 seconds, and again it is cooled to
30 to 40. Cool means cooled basically to the ambient temperature, 30 degrees Celsius approximately.
Okay, that means milk is heated continuously, and once it attains above 100 degrees centigrade, it is retained for 3-4 seconds, and that is cooled again to 30-40 degrees centigrade.
Yes.
But for heating, holding time means that the above 100 degree temperature milk is kept heated for just 3-4 seconds like that.
3-4 seconds only, but for general pasteurization process, which is carried out at 72.5, there we hold the milk for 15 seconds. So depending upon the temperature which we use, the holding time will get reduced. So we can do pasteurization even at 60-65 degrees Celsius. There the holding time will be much higher, that is 30 minutes. So that depends on the temperature at which we are doing the process. And this specifically this ultra high treatment we do for the milk which is being stored without any refrigeration. That, for example, what we buy through this Tetra packs. You must have observed they are kept outside the refrigerator, just like the normal product. So it doesn't require any refrigeration unless and until it is being opened. It is having a very high shelf life also, starting from 3 months.
Okay, holding time means it is maintained at constant temperature for that particular amount of seconds.
Yes, yes. Actually, for that one arrangement is there, which is specifically called as holding tube. So that the milk is being passed for this 3 to 4 seconds.
Okay. And regarding the production of this butter and cream, it is, I think, very costly, I think. Is it costly?
No, actually that I cannot comment on the cost part of that, but it is being generally carried out in the dairy industry. Actually, for the production of this cream, we are having a centrifuge is there. From there, we separate this cream, and then this cream is being further processed for butter.
Okay, basically the cost of cream and ghee is greater than the ordinary milk. That is why I asked this question.
Yes, because it passes through a series of processes there.
Okay, that means from suppose from 1 liter of milk, hardly 100, 200
yes,
gram of cream is
for
obtained.
1 kilogram of cream, almost I think it is 15 liter or something like that. We need to.
Okay, okay, that is why it is costly.
Yes. It
okay, sir. Thank you.
Dr. Jayaprakash. Dr. Jayaprakash, do you have any question? Mr. Lakshmanan is.
Yeah. Yeah, Dr. Doctor, what are the energy recovery from the heat that is after the produce? What are the energy recovery measures that you employ?
From this production of this milk?
Production of two things. One is the spray dryer. You go at a very high temperature of 150 to 200.
Yes.
Number one. And number two, in the CIP, the temperatures are quite high. Are there any recovery measures?
Yes, it is there. Right now, I am not having an image of that. I will tell an example. For pasteurization, we heat the milk to 72 degrees Celsius or above that. So this after pasteurization, this has to be cooled to 4 degrees Celsius.
So that I understand. I know.
Yes. Yeah.
I'm not talking about that. I'm talking about the system independent of the milk operation. For example, the spray drying, you are taking it up to 150 to 200. Are there any energy recovery measures possible from those high temperature air that you are using?
Yes, that will be used to reheat the supply of other components into the system. That's what I'm telling. Just if this in spray dryer, whatever the gas is being exit from that system, it is used to the preheat the product which is coming into the dryer.
How do you do that?
What is that?
How do you do that?
We have heat recovery unit for that. It is there. So
milk powder is very sticky, right?
No. From product, we are for that milk powder, we are not using that kind of heat recovery. But that's what I'm telling. That can be easily done in the case of this pasteurization process and all. For powder, we are not using that. Powder,
You're wasting their energy. Huh?
No. We are not.
Heat at all because high grade heat is basically a very high grade heat.
Yes, but for that from powder we are not using. But whatever the gas which is being exit from that system, that is being used because when powder production, we don't allow the temperature of that that hot dry air to go below 100 degrees Celsius and all. So that air is being used to preheat other components, but powder is not being used for that, not used for any heat recovery.
Okay, what about CIP? Is there any
Yes,
measures
for
or
CIP, this is there. The return circuit is being used to preheat the other circuit. That is there.
with a simple PHE?
Yes, simple braced plate heat exchanger only. For example, if you see the these kind of, it will braced plate heat exchanger, they will be having 3 compartments. It will be having a heating, it will be having a heat recovery compartment, it will be having a cooling compartment. It comes in a bank. So
Okay.
braced plate heaters only, heat exchangers are generally used for these applications. And that is the base. Yes, please tell me. Hello, am I audible?
Yes, you are audible.
Okay.
Mr. Sunil Kumar, you have questions? Mr. Sunil Kumar, am I audible?
Sunil, yes.
Yeah, Dr. Vaishak, I have 2 questions.
Yes.
One is for converting milk to curd or
Yes.
to khoya. Do we require this pasteurization?
Yes.
And for khoya, what is the temperature requirement and for how long for converting milk to the khoya?
Okay, I cannot answer that completely because I'm not an expert of that process. But for that curd manufacturing, the temperature for this heat treatment process, it is being specified above 90 degrees Celsius. But I am not remembering what is the time period for that. But temperature is above 90 degree. 92, I guess. Exact value, I think it is 92. But for how long, that I'm not sure.
But for both process, we do pasteurization or directly milk we just heat it and
No. For this dairy application, for this processing plant, pasteurization is there. Directly we don't use that. Pasteurization process is. And
for paneer, converting milk to paneer.
No, that I'm not sure. About that.
Okay. Thank you.
Okay.
Okay. If no one has any questions, let's move on to the last session of today's workshop presentation. Last session presentation on freezing application with CO2 for maritime sector, which will be presented by Dr. Arun B S. Arun B S is a postdoc fellow from the ICAR Central Institute of Research Technology, Kochi. Dr. Arun has devoted his entire professional career to developing energy efficient air conditioning and heat transfer technologies. He has carried out research on the evaporative cooling process and investigated new system and apparatus for air conditioning. He was awarded PhD from National Institute of Technology, Trichy, India. In this capacity, he delivered lecture on thermodynamics, refrigeration, air conditioning, and heat and mass transfer. He has also published research papers in reputed journals. Currently, he is working on ammonia CO2 cascade refrigeration system for seafood deep freezing applications. So I request Dr. Arun B S to proceed with the presentation on freezing application with CO2 for the maritime application.
Yes. Thank you, Vinod. So hope my presentation is visible. Yeah.
Yes, Arun, you can continue.
Yes. So I'll be switching off my video camera to have a better network connectivity. Okay. So we'll start with the session about the freezing application with CO2 for marine applications. So myself, Arun. So I'm the postdoc researcher from CIFT Kochi. So just 1 minute. Yeah. So about this institution, that is CIFT, Central Institute of Fisheries Technology. This institution was established in around 1950. It's a national center in the country where the research in all disciplines relating to fish and fish processing is being undertaken. And they have several research centers which functioning at Gujarat, Visakhapatnam, and Mumbai. And here in this institution, there are certain divisions where researchers are carried out. So these are fishing technology division, fishing process, biochemistry and nutrition, quality assurance and management, microbiology and fermentation and biotechnology division, engineering division, extension information and statistics division. And I am from this engineering division. So as in the previous talks, we have discussed about the I&D activities. And in the I&D activities, we have stressed about two things. That is, one is the installation of a educational training unit. So that educational training unit will be established in CIFT, where the vendors or the suppliers and who are interested in this field can come and learn and get a training from this system. And the other one is that we'll be installing an actual CO2 system in a seafood processing industry. And apart that, we are also looking for a fishing vessel where we can install this CO2 system. So at first, we'll just see about the seafood processing industry, where this CO2 system can be installed. So below here, you can see some images of the seafood processing methods that they are used, where the shrimps or prawns have been frozen and been packed. So at first, we'll just see the different types of freezers that are used in this seafood processing industry. So, when we talk about the freezer, it is actually the indoor component where it will be having the evaporator coils. Okay, so these evaporator coils, the machinery, everything will be come along with this system, and the other will be the condensing unit that will place outside the this main freezer component. So there are different types of freezers that are basically used. Here you can see the freezers that is used are air blast freezers, plate freezers, cryogenic freezers, bed freezers, immersion freezers, tunnel freezers, and spiral freezers. This tunnel freezer and spiral freezers will support another type of freezing process, that is IQF, or it is also known as individual cube freezing. So in the next section, next slide, we can discuss about this type of freezers. So I won't be discussing all the type of freezers. We'll be just see the commonly used freezers that are used in the seafood industry, especially in Kochi, Mumbai, in these areas. Now, how these freezers have been selected? How do we select which freezer is necessary? So this selection is actually done. Just 1 minute. Yeah. So this selection is actually done depending upon the product quality and the freezing rate that is required, the type and shape of the product that is required, and the packaging that is required, then the flexibility required in freezing, whether we have to go for a quick or go for a blast freezing, and the cost of freezing. So these are the different types of the freezers. So initially first one, that is the air blast freezer, which is commonly used. Here you can see the image of the air blast freezer. So in this air blast freezer, a forced air is circulated over the fish at a temperature of -42 degrees Celsius to 35 degrees Celsius at a velocity of 1.5 to 4 meters per second. And the fishes will be stored inside a tray and that will be pushed inside this freezing compartment. So this type of freezers are a simple freezer with a low investment, and it is suitable for any type of fishes. You can have irregular shaped products in these freezers. But this the disadvantage of this freezer is that this blast freezer are very slow in freezing, and it needs more manpower to actually to load the tray and push inside the freezer. The next one is another type of freezer, that is plate freezer. So in this plate freezer, you can see there will be the plates in this system, and in this plate the process or whatever the fish that is packed between the flat hollow refrigerated metal plates, and they will be pressed tightly. So it will be pressed in such a way that there won't be any air gap between or air resistance in the cooling. So efficient cooling can be obtained. These plates can be of different types. It can be a horizontal plate or a vertical plate. Mostly in the seafood industry in Kochi and this area, you can see they will be using mostly horizontal plate. But for a bulk, larger products, they can go for a vertical system. And the disadvantage of this system is that you cannot go for a irregular shaped seafoods. The next one is called a spiral blast freezer. Now, this spiral blast freezer actually supports the another type of freezing mechanism that is called IQF. The previous freezers which you have seen, it is actually a batch freezing process. That means you will have a batch of fishes or seafood that will be loaded inside the freezer for about a downtime of 4 to 5 hours. Then after that, you'll remove that batch. Then again, you will load the second batch. But in the case of this type of freezers, it will be a continuous process. There won't be any batch method. So it will be a continuous process where your seafood will be loaded. So here you can see an image of a spiral freezer. So this spiral freezer is nothing but it will be having a conveyor belt that is built around a central supporting structure, so that your area can be or the belt area will be having a large surface area in a small space. And this system is a good solution for delicate products, and it minimizes the product damage at the transfer point, and it is having a high capacity, and as I told, it is a continuous production, and you don't need to have a manpower because the conveyor belt itself will take care of most of the process. Then next, another type of freezer that is mostly used, that is called tunnel freezer. So this tunnel freezer also supports the IQF method, that is the individual cube freezing, where each and individual fish products will be frozen. So here you can see the image of an tunnel freezer, where there will be the fan coils. The fan coils along with the evaporator, fan along with the evaporator coils. It can be either on the top or can be on the bottom, where the air will be blasted on the products that will be moving along the conveyor belt. So this freezer, it can have is very capable of handling around 0.5 to 20 tons of seafoods per hour. So this tunnel freezer is ensure the highest degree of the IQF quality and the supreme freezing flexibility for small product range. And this freezer can actually be customized for according to the necessity of the seafood processing industry or the end user. Now, in the seafood industry, instead of going for the full CO2 system, we are going for the cascade system, that is the ammonia CO2 cascade system. Now, one of the reasons which we cannot go for a full CO2 system is that the heat recovery requirement in the seafood industry is very low. Mostly they are going for the freezing and cold storage requirements. So that's why an ammonia cascade system will be very efficient. And apart from that, we are going for a deep freezing process that is around -40, -43 degrees Celsius. So we will be choosing for this ammonia cascade system. Now, why this ammonia cascade system? As you know, these things has been already discussed, but we'll just go through that the ammonia charge that is required. As you know, the ammonia is toxic in nature. So this ammonia charge that is required will be very low, and the overall maintenance is very low. And you don't need to have a cooling setup for the low side compressors. The cost of the refrigerant, that's the CO2 refrigerant, is very low. And the CO2 system are always operating at a positive pressure. So that is one of the another important criteria we have to note, that the CO2 system will be operating at positive pressure, whereas a full ammonia system will be operating at a -40 degrees Celsius below the atmospheric pressure. So when the system is operating below the atmospheric pressure, what happens is that there will be a chance for moisture ingression, or the chance for moisture to enter into the system, which may cause failure for system. So up to a temperature of -20 degrees Celsius, you can have the full ammonia system. Below that, the positive pressure system will be very effective. And the other advantage is that this ammonia won't be present in the food processing area where they will be loading the seafood and everything. It will be in a separate engine room, and the CO2 will be in the seafood processing area. And as you know, the CO2 is non-flammable, non-hazard, and you can also adopt a pumped system with CO2. So normally in these seafood industries, they will be having a pumped refrigerant system. That means there will be a liquid receiver or a circulating tank from which the refrigerant or even this ammonia will be pumped to the evaporator using a pump. So it has its own benefit. That is in the seafood industry or in the freezer, it has to go to a process called defrosting. So during defrosting, if the refrigerant is present inside the coils, the evaporator coils, it will actually raise the pressure there and it will cause the failure, total failure. So during defrosting process, there should not be any refrigerant present inside the coil. So it can be pumped back to the liquid receiver and the defrosting can be taking place. And here you can see a graphical representation where we have compared the conventional system, that is a single stage ammonia system, and there is a two-stage ammonia system. And we have compared it with our proposed ammonia CO2 cascade system. And at a very low temperature, that is at -40 degrees Celsius, the COP of ammonia cascade system is very high. And apart from that, you're getting the benefit of a positive pressure. So it is actually very usable for our seafood application. And now let's see about this. Why should we actually move to this level? Even though there are various type of ammonia system, the two-stage ammonia system, which are very efficient or effective. So one of the criteria is that the size really matters. So here you can see a comparison of the ammonia system with our CO2 system and with the freon system. In case of our CO2 system for an refrigeration system that is around 100 kilowatt, we can see the pipe dimension, that is the suction line, the discharge line. The dimension of the piping diameter is very low, but you need to use a thick pipe, but with a lower diameter, so that the system becomes compact. And here you can see the suction diameter of the ammonia system, it's around 100 mm. That is because of course, in the case of a ammonia system, your specific volume will increase at the suction side, so you have to have a larger pipe. And if you're comparing with the compressors, I have arranged the compressors in related to its size. So you can see the size of the ammonia compressors. They are very large, and then the freon compressor, then the CO2 compressors. It is comparatively very slow, so very low. So you can actually have a compact system with the CO2 arrangements. But you have to note that maybe you may require more than 2 compressors for a specific capacity. But even though if you're installing 2 or 3 CO2 compressors, it can be actually installed in a very compact mode rather than having this bulky ammonia system. So yes, the size matters in the seafood industry, especially in areas like Kochi, where the space is actually constrained, and the seafood industries are just in a location where they have the backwater and the sea. So the space is a constraint for them. So you can actually remove this. So here you can see the photograph of an ammonia compressor. So you can see these bulky compressors which are having the larger diameter pipes. And in the proposed seafood industry, we could actually they are actually renovating the industry, and this compressor can be actually replaced, and they can have a new blast freezer or a IQ unit instead of this bulky compressors. Yeah. Now, what is this relevance of this CO2 cascade system, this ammonia CO2 cascade system, or simply I'll call it as the cascade system? So you can have a single evaporator arrangement for a single cooling. That is you can have the defreeze arrangement with a single evaporator that is around -40 degrees Celsius, and you can have a pumped arrangement. So this is the typical layout of an cascade system where you have the top cycle with the ammonia top cycle, then a cascade heat exchanger. Of course, you know all these things, basic things. Then you have the CO2 bottom cycle with a liquid receiver, and from the liquid receiver, the CO2 will be pumped to the evaporator for the freezing requirement. So here you can have a single evaporator arrangement, which we are following now. And apart from this, you can also have a multi-evaporator arrangement where you can have a cold storage unit and also a deep freezer. So the cold store will be at a temperature around -20 degrees Celsius, and the deep freezer can be maintained at -40 degrees Celsius. So the system is same, but you need to have two stage of expansion. At first, you can expand to the required cold storage temperature of -15 degrees Celsius. And after that, again, you can expand to the required temperature of -40 degrees Celsius. So with the CO2 system or with the cascade CO2 system, you can also have a multi-evaporator configuration. But under this project, under the IND project, or which we are going to install in the seafood industry, we are going for only a single evaporator configuration. So next, here you can see a full-fledged a cascade system. So this is a work from Pachi and so Johnson, who was working in Johnson Controls in 2017. So here you can see the full configuration. So we in previous lectures we have discussed about the cascade systems. But we'll see here. So I'm not going to the working side of this system, because most of you are already familiar with the working side of the cascade unit. We'll just see the different components that are being used and which is relevant to the seafood industry or for the freezing application in the seafood industry. So at the top cycle, here you can see on the right side, you have the ammonia system or the ammonia top cycle. And you will have the screw compressor. From the screw compressors, so mostly we'll be preferring for screw compressors so that you can have the benefit of liquid injection to reduce the temperature of screw compressors. So from the screw compressors, it goes to the condensers, and from the condenser to the expansion valve, and this go to the cascade heat exchanger. And from the cascade heat exchanger, it will again go back to the cycle will get complete. And from the cascade heat exchanger, where our CO2 will be condensed, and it goes to the expansion valve, and the liquid will be collected inside a liquid reservoir, or you can also call it as a, typically in the seafood industry, they call it as a circulation tank, CO2 circulation tank, so, or the NH ammonia circulation tank. So it will be entering into the CO2 circulation tank. And from the CO2 circulation tank, it will be pumped to the evaporator using two CO2 pump. So you can see the two CO2 pumps at the bottom, where it will be pumped to the evaporator. So you can have your vertical plate freezers, and also if you have the requirement of a cold storage, that also you can have it. And after that, it again goes back to the your liquid receiver, from which the CO2 compressor will suck the vapors and compress it back to again as the cycle completes. So this is the basic layout of an ammonia CO2 cascade system that can be utilized, and which we also have proposed for the seafood industry. Now there are two things which you have to, while you are designing this system, you have to take care of two things. That is, you may have a requirement for defrosting. So in last lecture also there are some participants who were asking what is the necessity of defrosting. So I think Maya sir has explained what is the necessity of defrosting. So defrosting will be needed. It's not just with the seafood industry. For all the freezers, even with our household freezers, we need to have a defrosting setup to just to melt away our ices that is being deposited on the evaporator. So you need to take care of the defrosting section. So you can see the defrosting that has been defrosting lines that has been utilized, have been installed in this evaporator. So here the defrosting will be done by a process called hot gas bypass defrosting. So hot gas bypass is nothing but the hot gas from the discharge of the compressor will be taken, or the hot vapors from the compressor will be taken and will be sent into the instead of sending to the condenser side, it will be sent to the evaporator, where you will have the frost deposited and it can be melted away. So that also to be taken care. So, but during the hot gas defrosting, you have to take care that the pressure will be more. So your design pressure should be more. So you can see for without a hot gas defrosting, you can have the system at around a 35 bar maximum pressure. But if you're going for a hot gas defrosting, you should design a system for a 50 bar pressure. Then the other parameter which you have to see while designing a cascade system is to take care of the standstill pressure. So normally the standstill pressure, which is nothing but when you switch down the system, and if you are not using your operating system for more than 2-3 days, what will happen is that you have designed this system for a maximum to a pressure of 35 bar. So when the system is not operating, it will be at equilibrium with your ambient temperature, and your pressure will correspondingly start to rise up, so that your designed pressure or the pipe pressure will be something around 50 bar, but at 30 bar your pressure will rise up to 70 bar. So that will actually affect the system. So to overcome that, you can go for a standstill cooling unit. So this standstill cooling will be can be a small cooling unit around 3 kilowatt, 3 to 5 kilowatt. In some of the system, they are going for a freon unit, but this can be replaced with a natural refrigerant like a propane unit, a small propane unit, so that the whole system will remain with a natural refrigerants. So this is the basic layout of a ammonia CO2 system. So now let's see what is the other thing that is actually required. As I said, this system required, or the freezers will be requiring defrosting setup or defrosting arrangement. Now there are different types of defrosting that has been used. So these are the different types of defrosting. So you can go for natural defrosting or a water flow spray defrosting. So this is nothing but you will just switch off the freezer, so that whatever the existing ice that has been deposited on the evaporator will be melt and will go. Or apart from that, you can actually spray water also on the evaporator to remove the ice. The next type of defrosting that is used is called electric defrosting. So in electric defrosting, you can have an electric coils. So it is actually a low investment method. You can have the electric coils, and the electric coils will heat up the frost that is formed, and it will melt it away. That was done. But in this case, your energy consumption will be more. And there is another one method that is called reverse cycle defrosting. So this reverse cycle defrosting is normally carried in the case of an heat pump that is used where your evaporator will be frosted. So you can actually reverse the whole cycle to defrost the system, which cannot be adopted here. So in our case, we'll be going for a hot gas bypass defrosting, where you will take and just 1 minute. Yeah, so we'll adopt a hot gas bypassing defrosting method. So here you can see the image of an hot bypass defrosting method that is normally adopted in the freezers. So to have this system, the hot gas bypassing system, this hot gas can only be used in a system that is having multi evaporators. At least we should have 3 evaporators. So during this hot gas defrosting, at least 2 evaporators must do its work, that is the cooling work, and the 1 evaporator can be go for defrosting. And this also this hot gas bypass defrosting, it depends upon the amount of heat that is required and the mass flow rate of the refrigerant that will be flowing inside the for the different side. So how you can decide the amount of heat that is required is you can measure the thickness of the ice that is deposited, an average measurement of the ice that is being deposited, and you can see the total surface area of the evaporator, and can get the mass of ice. From the mass of ice, you can get the amount of heat that is required actually to melt the ice. With respect to that, you can actually determine your temperature, and also you can determine the mass flow rate of the refrigerant, the CO2 refrigerant that is required for hot gas defrosting. So here you can see the image of an hot gas bypass defrosting. From the compressor itself, you will have a bypass. From that, the hot gas will be taken, and it will be given to the exit of the evaporator. Normally, this is done to avoid the hammering effect and other effects. So it will be given to the exit of the evaporator. And after that, it will go inside the evaporator, and it will exchange heat with the ice that is deposited on the evaporator. And this hot gas will condense, and this condensed hot gas or the condensed vapor of CO2 will go to the pressure release valve, because here the evaporator will be at a higher pressure because it directly comes from the compressor, and it goes to the pressure release valve, and then the pressure will be lowered to the pressure of the liquid receiver, and the liquid will be, the CO2 liquid will be stored in the liquid. From there, again the vapors will be taken. So this next cycle of vapors will come from the cooling cycle that is actually operating in the freezers. So this is how the hot gas bypass defrosting is carried out in the freezer. So these are the so this is one of the things that you need to consider while designing the freezer. So now let's go to our system, that the system we have proposed. So we have proposed a blast freezer of a 62 kilowatt. So here you can see the bottom cycle of the blast freezer. That is the bottom CO2 cycle which we have proposed for the freezer. So he can have the compressor rack. This is a compressor rack here at 22 kilowatt. And it goes to the oil separator and then to the cascade heat exchanger around 85 kilowatt. And it can be expanded. Then the CO2 is being expanded to CO2 circulation tank. You can have an intermediate receiver here in between, but you can or else you can directly expand it to the CO2 circulation tank to reduce your cost. That can be done. And from the CO2 circulation tank that is stored, that will be having around minus 43 degrees Celsius, around 9 bar pressure. The liquid will be pumped to your evaporator. And these are the evaporator coils. So those are basically the fan coil unit which we can see. And this fan can be arranged. Fan can have different arrangement. You can have 4 fan arrangement, 6 fan arrangement. It depends upon the requirement or the airflow rate. And the vapor will be sent back to our liquid receiver, from which the compressor can take the vapors again. So in the case of the blast freezer, as I said, the blast freezer will be going through a batch process. In the batch process, you load the fish for like a 4 hours. Your downtime will be, your full time will be 4 hours. Then again, after the 4 hours, you will go for the next batch of fish. So in between that, if suppose the moisture content of the fish is high, you have to go for the method that is called the defrosting method. Now, as I shown before, the defrosting technique, that is the hot gas bypass defrosting technique, where your hot gas is directly taken from the compressor. But here in the cascade system, we can't go for that, because in the full ammonia system, you can directly take ammonia from your compressor and give it to the evaporator. But here you can't do that process, because you are having 2 different type of refrigerants. So in this case, what you have to do is that you can see from the, if you are suppose you are taking the hot gas from the exit of the discharge of the compressor, you can see the condensation temperature, it is around minus 8 degrees Celsius for the cascade heat exchanger. So at 28 bar. So you can't do your defrosting at this temperature. So actually you have to increase your pressure to a higher bar. So in case of a hot gas defrosting for a CO2 cascade system, you need to have a separate compressor that we called as a defrost compressor. So this defrost compressor, you can either connect it directly to the outlet of your discharge of your compressor, or you can take the boil of vapor from the cascade heat exchanger. So you need to have a defrost compressor to increase the pressure, so that the pressure goes above your 0 degrees Celsius up to 5 degrees Celsius, so that you can obtain your defrosting, and that will be sent to the evaporator. So that was a blast freezer which we have proposed. And apart from blast freezer, we have also proposed another system, that is a tunnel freezer, an IQ for 90 kilowatt. So this is a tunnel freezer, which I have explained in the first slides. So in the tunnel freezer, you will have a freezing chamber. And we are having a hardening chamber. Suppose this is a 90 kilowatt freezer, you can have a 60-30. You can divide the capacity here. The temperature will be mostly same on the 2 section. So what happens is that the fishes will be frozen here, and you will have a water dip here in this section. So the frozen fish will go to the water dip and goes to the hardening chamber. So what happens is that the water that is around the fish will get hardened, and you will get a hardened or enclosed hardened fish product. So that is being done in the IQF, and this shows our proposed system of 90 kilowatt proposed system for the seafood industry. So most of the things remain same here. You have your top cycle, the top ammonia cycle here, and it goes to the cascade heat exchanger. So the cascade heat exchanger can be either a PHE, that is the plate heat exchanger, or it can be also a shell and tube heat exchanger. It depends upon your requirement. And then bottom cycle, you have the same arrangement. There will be a compressor rack, the oil separator, and this will be expanded to our circulation tank, and using a pump, it goes to the evaporator, and the cycle continues. Now, in this case, in the case of an IQF unit, you necessarily don't need to have an defrosting arrangement, because it is a continuous process. Unlike the blast freezer, where you have a batch process, where in between the batches, you need to have a defrosting. In the case of an IQF unit, you can carry out this freezing process continuously for a day, and in the end of the day you can just switch off the machine and naturally it will get defrosted. So we are actually we have proposed with this system, or we are actually working on this system for this IND plus project. And there is another one proposal which we are seeing in this marine sector, that is for the fishing vessel. So we have identified a fishing vessel. So here you can see the image of the fishing vessel. So this is a sub 50-meter fishing vessel, and the fishing vessel will be having a deck where the ice will be, where you can have a chamber where the fish will be stored, which will be a cooled area. But normally, conventionally, what they do is that, what fishermen do is that they will be loading this deck with ice, and they will be storing their fish. But what we are proposing for a refrigeration system or a refrigeration fish hold or fish chamber for this deck based upon CO2. So for this, we have identified a fishing vessel. So this fishing vessel is actually built by Kochi shipyard under some government of India scheme. And one of these fishing vessel will be modified to our CO2 refrigerated fish hold. So this fishing vessel is having two different refrigeration apparatus. One is called slurry ice system, which in last lecture Christina Madam has explained, and that it will be having another one apparatus refrigeration system that is called refrigerated for medium fish hold, which is normally they are using the term fish hold or the fish holding chamber at around -4 degrees Celsius. So this is about the details about the fishing vessel. So this fishing vessel is having some modern navigation system, some communication equipment, and an advanced net hauling system, and other facilities which is the 3 ton per day capacity sea water slurry ice system, and a 10 kilowatt stainless steel insulated fish hold to preserve the fish catch at -4 degrees Celsius. So this fishing vessel can have either of the system, either it can have a 3 ton per day capacity seawater slurry ice system, or it can have a 10 kilowatt fish hold at -4 degrees Celsius, where the temperature of the evaporator will be around -10 degrees Celsius. So for that, we have proposed a CO2 refrigeration system, a 10 kilowatt CO2 refrigeration system. So this is a layout, a system that is being proposed by Gustav Lawrence. So in this system, it is called a low pressure receiver system. So as the fishing vessel, the space is a constrained thing, and moreover, the cooling capacity is very low. We are not going for an ejector model. And apart from that, the condenser is a water-cooled condenser that will be operating at the seawater temperature of 28 degrees Celsius. So it is in 28 to 30 degrees Celsius. So it will be on the zone, on the critical point zone. So we have proposed for a low-pressure receiver system without any intermediate receiver and with a high-pressure expansion valve, so that the vapor, this will be expanded directly. So it won't be fully liquid; it will be liquid and vapor, and it goes to the expansion device and inside the evaporator, and it will end up inside the low-pressure receiver. So inside the low-pressure receiver, there will be a certain amount of liquid and also the vapor, and the vapor will be taken care by the compressor. So with this arrangement, we are able to actually reduce the cost of oil circulation, and apart from that, the compressor can also be cooled using the liquid injection. So the liquid injection process can be actually adopted here, so that the liquid from whatever the liquid that has been obtained at this low pressure receiver can be pumped to the CO2 compressor. So by the liquid injection, the temperature of the CO2 compressor can be brought down, and along with the liquid injection, the lubricant also, the refrigerant, the oil also will be moving into the compressor. So with this arrangement, we can have a cost-effective, simple system for the fishing vessels. That is also proposed under this INDE plus project. So these are the 2 demonstration sites which we will be installing in future under CIFT. And next to the participants, I will just show you some simplified tools that can be used. So whatever we have talked before, we have talked about different types of system and modeling everything. So you can use some simplified tools to understand our CO2 system rather than just doing it mathematically. You will have some difficulty. So you can use tools like MATLAB, Scilab, and a less powerful tool that is called engineering equation solver is available. You can use this tool to actually to put your equation, the CO2 equation, the your ammonia equations, your freon or whatever it may be. You can select the refrigerant and you can use your enthalpy equations to simulate the results. So normally you can go for your enthalpy equations where you need to assume your isentropic efficiency of the compressor or the volumetric efficiency compressor in that way. But you can actually make it more realistic, or can go to a little bit rather than theoretical. You can actually select a compressor and you can do the simulation based on the compressor. So for that you can actually download the compressor software. So these compressors are the CO2 compressors are manufactured by companies like Dorin and Bitzer. So they have their own softwares. So in these softwares you can actually put your values, that is whatever your cooling capacity, whatever is your evaporating temperature, condensation temperature, all this can be input into this software and you will get your required compressors. You can have different type of compressors depending on different mass flow rate, and it will also show the envelope, the temperature envelope inside which the compressor will work. And apart from this, you can also have the coefficients for these compressors. So you can get the coefficients of these compressors. Here you can see this is a compressor model of CDS2410B, and it is having a polynomial equation, and you can get different coefficients for this compressor. And based on this coefficient of compressor, you can actually calculate the cooling capacity, the power, the mass flow rate that will be required for the compressor. So you can actually keep your mathematical modeling a little bit realistic. So I think I request the audience, students, especially students, to go through this method and analyze our systems. Yeah, so the conclusion for our work, or the IND work, that is we will have the demonstration sites that will be purchased by the end user. The IND plus team will give support to the end user for designing technical combination the first year, and we'll have some joint publication which are the IND plus goals, and we'll do this to share the knowledge how to take this forward and encourage others to start a similar type of development. We'll have a data management plan which will be established in agreement with this end user. And apart from this, we'll have this demonstration site. It will be completely operated by the end user. And we'll also including the local vendors during the manufacturing process. So these local vendors will be delivering the entire units, and they will also do the servicing and maintenance. So even after the end of this IND project, they can carry out with the service. So this is regarding the application of CO2 in marine division. Yeah, so these are the reference. Yeah, thank you.
Thank you, Dr. Arun B S, for the excellent presentation. If any of the participants have any questions, please ask. Dr. Kamal Jyoti.
Hello. Hello.
Yeah. Yes, sir. Yes, sir.
Doctor, I didn't exactly understand the hot gas defrost you are explaining.
What are?
Hot gas defrost.
Hot gas defrost. Yes, sir.
It is not. I didn't
Yes,
see
sir.
where the gas is going or the liquid is going after the evaporator. That part is not clear.
So should I again? Okay, sir. I will again present it.
Or you can at least reconsider that. I was not sure it is the right.
Yes, sir. I'll just show it you.
Yeah.
So yeah. So can you see the screen, sir?
Yeah.
Yeah. So it's visible now. So,
it is visible.
Yeah. So the idea is basically this. You can see a compressor here.
Yep.
Yeah, you can see the compressor here. So this compressor is actually taking vapors from your liquid receiver, whatever after the evaporator, whatever the vapors that coming, and this vapor will be bypassed. So there will be a bypass valve here, a hot gas bypass valve. So this hot gas will be bypassed to your evaporator. So the hot gas will be having that temperature and it will be having a sufficient mass flow rate. So this will be bypassed to evaporator, and normally you can give it to the inlet of the evaporator or even the outlet of the evaporator. So this is the evaporator here. You can either give it to the inlet or outlet, but the normal procedure that is being used in the industry is that you will give it to the outlet of the evaporator, and then it enters into the evaporator. The hot gas will be entering into the evaporator. So when the hot gas entering the evaporator, whatever the ice that is deposited on the evaporator coils, whatever the frost that's deposited on the evaporator coil will melt down, and this there will be a heat exchange, and this hot gas will get condensed. It won't be fully liquid, but partially liquid vapor will be formed, and that will be again going back to the liquid receiver. So that's a simple mechanism that is used in the seafood
That
industry.
is my question.
Yes, sir.
You are showing that as the pump, say, the liquid going back is toward the pump discharge. How will it flow?
It is not pumped. It is not pumped. It is going back to this is the route. This is the path. Can you see my mouse pointer?
Okay, I'll put it this way. Your
Yeah,
hot gas inlet is coming. It is coming into the drain pan. And
Yeah.
from the drain pan, it defrosts it, then goes and it's a top feed evaporator. That's why you are injecting it in the top. Now, liquid vapor mixture will come back.
Exit of the operator. Yes, sir.
Liquid
Yes, sir.
vapor is coming back at the outlet at the
Yeah.
bottom.
Yeah.
Where does it go?
It again
How does
goes
it
back to the receiver. You can see the yellow dotted line. You can see the dotted line here. Can you see the dotted line? Is the
I'm
dotted line
seeing,
visible?
but okay, I'll put it other way around. Which is your liquid feed line to the evaporator?
Liquid?
Where is the liquid feeding the evaporator?
So this is the liquid. This is liquid that's feeding evaporator, but you don't need to feed the liquid to evaporator.
Now, during defrost, you don't need to.
You don't need
during
because
refrigeration, you need to feed.
yes. During
Where is
defrost,
that liquid line?
Yes. During defrosting, you don't, because it is not cooling. It is actually.
Okay, sorry, I think you are not getting it.
Yes, sir.
Sometime I'll explain you that your explanation is not correct. Even the diagram is not correct. See, I don't have the pointer. See, you are showing the liquid going back through the liquid feed line. It is not correct. There is a bypass line which will feed liquid from the evaporator outlet to the it will feed after the pressure control valve. You are not showing it. Anyway, it's okay.
Yeah.
I didn't mean
Fully it is not shown.
to
For
insult you. I
simplicity,
just wanted to
I have
highlight.
kept it simple, sir. If you want to show in detail, I can show it. We have a full diagram. For simplicity, we have made it this way.
This is not correct.
Yeah. Okay, sir. Thank you for pointing.
It is not
Thank you for pointing
adding
it
up
out.
1 + 1.
Yes. Yeah, I understand.
Sorry, take it positively.
Understood. Yes. I will change it.
Yeah. Thank you.
Hello, Dr. Arun. Just you enlarge it in zoom view where you are giving bypass there top line where you have written pressure controlled on top.
Yes, sir.
Just zoom it. I think Kamasa is getting confused from there. It is not visible. It is connected to that.
1 minute, sir. Yes.
Yeah, zoom it little more.
To zoom it in
Can
the
you
sense,
zoom?
it is a PPT.
No, you thumb in the this one normal mode and then zoom it, not in the presentation mode.
Not in the normal.
Yeah.
And then zoom it. Yeah.
Yeah,
So,
that's maximum possible.
yeah. Okay. So Kamasa, here it is the dotted line you are seeing, red color.
Yeah.
That liquid is following and it is coming to the liquid, this one, vapor line. You can see here, top. And then it is going to a receiver. So it is not coming to the blue color line and it is going to the pump. So defrosting is coming from it is from outlet of the evaporator. Hot gas is entering in the evaporator and coming from the liquid line that was feeding to the evaporator. It is coming from that way and it is following the red color path, dotted path. And from here it is the vapor line, what it was there in the normal cycle, it was going connecting to that. And then from here, it is coming to the receiver.
Yeah.
Yes. Kamasa, I think
that is correct. This is correct. This is exactly what it is.
Yes, that can be changed.
So it was not visible, Arun. So that's why Kamasa got confused.
Okay.
Just a little bit, you can give the distance between two lines. So it will be easy to
It will be
understand.
easy to disable. Yeah. I have some other figures. This is just for the presentation we have done it like. Okay.
Yeah.
Yeah. Thank you for pointing it out.
Yes, Dr. Arun sir, may I ask you a question?
Yes, sir. Yes.
Sir, generally, when we talk about a CO2 system, when it is not going to be used for a longer duration, like 15 days, month, or 2 months, its standing pressure is going to be very high, in the range of maybe 80 bar or 90 bar. So, what precautions we are supposed to take to handle that higher pressure? Because I have read somewhere that the people are using a fed vessel and to accommodate that high pressure. So can you comment on this? What is it? Fed vessel?
They are using a fired vessel.
Fed vessel, FADE, fed vessel.
Fed vessel. So I am not familiar with that point. For the standstill pressure, there are only two methods that are currently used. One method is to have a backup system to cool this receiver to maintain our stand pressure. The next one is to design our full system for the higher pressure, higher bar.
Okay.
We can't have any other arrangement because it practically doesn't make sense. Yes.
Okay, sir. I have read somewhere in a history journals. That's why I'm asking you. Okay.
So maybe some new researches are going on, but we didn't explore that much.
Okay, sir. And second question is there any standards for designing a CO2 refrigeration system available currently? Like for ammonia, we have a standards. Association of Ammonia Refrigeration has published a standard recently in India, which we are supposed to follow. And for international level, that is an IIAR standards for ammonia refrigeration. So is there any standards available for CO2 refrigeration system design?
Yes, sir. So it's currently for the seafood industry. We are actually, this is the first time that has been done. So, yeah. So it has to come from this project.
Okay, sir.
Yes.
Thank you.
Yes.
Thank you.
Yeah, Dr. Arun, Lakshman here. I had one question on defrosting. Instead of having a separate compressor, CO2 compressor for defrost, why don't you have brine glycol solution pump through the?
Yes, sir. That will also be an excellent idea. If you need to cut the cost, you can have a glycol pump also. That's a good idea.
In fact, the heat can come from the ammonia system with a plate type heat exchanger.
Yes, sir. Yes, sir. That's a good idea.
There is a high grade heat also, so that is sufficient for defrosting.
That can be. I think this kind of techniques also are adopted. There are some seafood industries in Western countries in Europe. They are using this kind of technique, glycol technique.
Yep.
Yeah.
Thank you.
Yes, sir.
Mr. Chirag Kumar.
Hello.
Yes, sir.
Hello.
Hello.
Hello. Am I audible?
Yes, sir. You are audible.
Sir, you can continue. You are audible.
Sir, in the compressor, what fuel have been used here for fishing?
For fishing?
In the in the compressor, means from where the power is obtained?
Power in the fishing vessel. You are asking for the fishing vessel.
Right, sir.
Yeah. So the power will be obtained from the generator, sir. The genset. There will be
diesel generator.
Diesel generator, of course, sir.
Okay.
Yeah.
And what is the main advantage of this CO2 refrigerant fishing compared to other?
Currently, in India, we don't have a fishing vessel with a refrigeration system. That is a small fishing vessel around below 15 meters. We won't be having a reference system. What they do is that they load the ice from the shore and they go for fishing.
Okay,
So having a reference system is a first time. So we are proposing that to be CO2. Yeah, so that we can follow the green path.
That means with the help of CO2 refrigerant, you are producing ice by using generator as compressor.
No need to produce ice, sir. We can have the refrigerator inside the fishing vessel.
Okay, in this
it's not normal cold storage, or you can call it as a fish holding storage, where you can drop the fish. You don't need to have ice.
Okay, that means in the fishing vessel, this CO2 is circulated throughout for maintaining the temperature of the fish.
Yes, yes.
Okay, but you told ice is produced like that.
No, in normal case, conventionally, what they do is that this fishing vessel will be loaded with ice.
Okay,
they have a deck. Yeah, from the shore, they will be loading with ice blocks in the fishing vessel, and they will go for fishing to remain for 1 day. That's the conventional way they are doing. So the fishing vessel doesn't have any reference system, not even a freon system. Small fishing vessels. So
and we are
proposing something new. So let that be CO2.
Has it come to application now, or is just
no, sir. It has been the fishing boats have been manufactured, and we need to be install this system.
Okay.
Yeah.
That means with the help of CO2 as refrigerant, you will be designing a fishing vessel.
Yes.
On board.
On board, yes, sir.
Okay. Thank you.
Yes.
Okay, if no one has any questions, then I'm hand over to Dr. Siva Kumar.
Thank you, Vinod. So with this session, we are completing this 5-day workshop. So if participants wants to share something, any suggestions, any comments, you can please in this workshop. Then we will move on to conclude remarks. Hello, Dr. Kamal Jyoti.
Yes, sir.
Yes.
So good evening, everyone. So I registered for this workshop last week, and I was not aware how this CO2 will be used for refrigeration. So after this 5 days continuous lecture, I learned a lot, and what are the different avenues, the merits of carbon dioxide as the refrigerant. And that's all I have to say. And sir, I have one query. After how many days we will getting the e-certificate?
Maybe next week. We will try to send by next week. If not possible, in 2 weeks, we will going to send the e-certificates along with the recording video lecture links also.
Okay. So actually, I enjoyed this lectures a lot, and I learned a lot also. Thank you all.
Thank you. So any other participants? Okay. Thank you all. And now I'm handing over to Professor Pramod Kumar sir to give conclude remarks and vote of thanks. Pramod sir.
Yeah, thank you, Dr. Shiv Kumar Reddy. So my only request is if panelists can, if it is possible, to turn on the cameras so that at least the audience can see. We still have an exact 100 number of attendees, so at least they will know who are the speakers, and yeah, to all the participants, if it all the panelists, if you can
voice is breathing. So can you just check your voice once?
Thank you. All right. So at least you know whom to approach and how they look like.
Sorry, sir. Your voice is breathing bit. So can you check once?
So, am I audible? Is my audio?
No, sir. Still,
Still
it's not
it's
clear, sir.
breathing, sir. Not of this one. It's breathing, but
Is it because of the bandwidth? Insufficient bandwidth? Then we can switch off our videos.
Yeah, just a second.
Line only. So Pramod Kumar line only is weak because your
1 second.
Is this better?
now it's
One
fine, sir. Now it looks
better,
better.
sir.
Yeah, I continue, please.
Yeah. Is it better? Well, no.
No, sir.
Is it better now?
It's better. Okay. All right. So, yeah, thanks to all of you. And so I will just it's been a long day.
No, sir. Still.
And it's a Friday, so I'll keep it. 5-day session was a part of not audible. 1 second. Okay. Now?
Yes, sir.
Yes.
Yes, sir.
Muted. Muted.
You.
Sir, you are muted. Please unmute and speak, sir.
Yes, is this better now?
Yes,
Can you hear me?
Yes,
okay,
yes.
thank you. So I'm happy that the glitch is there in the internet towards the end of the session and not during the session. Okay. So first of all, we would like to thank SPARC. SPARC stands for Scheme for Promotion for Academic Research and Collaboration. And this 5-day session was a part of the SPARC program initiated by the Ministry of Human Resource Development, Government of India. So we are thankful to SPARC for giving us an opportunity to assimilate an excellent topic, which is of relevance at the right time now. So on this note, also I'd like to emphasize that this particular theme of natural refrigerants was selected by Professor Meyer, okay, based on the excellent collaboration that he had with Indeed, the NTNU team on the Indeed project, which was highly successful. So we are into the second phase of this Indie Plus, and most of the sessions that you had seen and the organizing participants as well as the session chairs were all from as a part of this Indie Plus collaboration. Okay. So I think, yes. So this 5 days was actually a very good intense workshop on natural refrigerants. So we had some very highly qualified and distinguished speakers, both from Norway and India. And we had in India, this was, as MHRD mandates that we should collectively work on a unified force. So in that sense, we were quite lucky that we had actually participants from all geographical locations of India, from east, north, west, and south. So we had speakers from Kerala, we had speakers from Rajasthan, from IIT Kharagpur, Professor Ram Gopal was there. Then we had Professor Maya from IIT Madras. Okay. So in that sense, it was a truly geographically free, session that we had. And we also had a speaker from Delhi who are looking at policies and how it is going to shape the future of usage of natural refrigerants in India. So on the first day, we had Professor Armin Hafner, who actually gave a talk about the Indy Plus program and how it is important for us to move towards natural refrigerant globally to arrest this climate change. And then yesterday we had another international session where we had two speakers from SINTEF who actually talked about energy storage. So the entire session was quite well balanced from both India and Europe. We had speakers from academia, we had speakers from industries, and we had also a speaker from Danfoss, thanks to Mr. Kamath. So, and applications covered quite a lot of very broad areas of topics, right from cooling, heating, and also cold storage and heat storage. So it was a rich blend of, sort of industrial applications which is really relevant, and yet retaining the enrichment of what an academic flavor would actually provide. So in that session, I think you cannot have anything better than this, where you have a lot of industry interaction, but yet it is academically rich. So the speakers had quite a lot of bit of speakers actually had good experience in building CO2 systems either in the lab. We had Professor Satyanarayana Seshadri, who actually talked about the upcoming Akshay Patra heat pumps project that was coming up. Then who also shared their own bit of manufacturing systems, the problems and the issues and how they face them. This is very important from this that drives the success of this technology, that the users really bring out what the real problems are, what they have faced, and how they have been overcome. So what it means is it instills confidence in the industry that apart from you, there are others who can actually help you arrest and face this challenge. Okay, so I would not want to stretch this. We are already 8 minutes, 7 o'clock on a Friday evening, so I would like to conclude it quickly. So to conclude, I would say this session is very important for the country and the world in general, as we are on the cusp of a major climate crisis. So, it's been raining in Bangalore for the past 2 days, and this is a season where we normally don't see any rains in Bangalore. So we are really witnessing this climate change. So we are seeing floods in areas where there was typically drought, and areas that have actually never had any floods, any rains, are now it's raining. So it's truly an issue of climate change, and that is really hitting us hard. So in that sense, we also have, this is a collective responsibility both from industry and academia. So I think while the push is coming from academia and somebody else and the government, I think it is also important for the industry to shoulder this responsibility and do a little bit for climate change, because it affects all of us. So it is our humble, you can hear the thunder out here in Bangalore, so which is not heard during this time. So if you look at, it's our humble request, to all the audience and the attendees, to do a fair bit of work on our side to create awareness on spreading the word on natural refrigerants. So whenever you buy an air conditioner or if you buy a refrigerator, please ask the person that what refrigerant does it use? Do you have an option for a natural refrigerant? And if we start looking at this change from the grassroots level, then people will create, there will be awareness and create that, oh, there is something called as natural refrigerant which is not harmful to the environment. Then this is the least bit that we can do. So, so in this, towards the end, I would like to thank the enormous effort put in by the session organizers, and particularly I would like to name Dr. Shiv Kumar and Professor Maya for putting this program together. It was a near flawless execution. And also IISc being a part of this SPARC team, we would like to thank all the session chairs, speakers, and also the audience. We clocked over 100 audience on every day. First day we had nearly 200, and and this was, we had a record number of participants for an online session. That shows that there is a lot of interest from all the participants. Okay, and even now, so I would like to particularly emphasize Dr. Kamal Jyoti had been asking questions in every session. That shows the attentiveness with which the audience participated. So I also would like to thank the NTNU team and the SINTEF team, especially Dr. Samarpreet Singh, who also put in a lot of effort in putting this program together. And finally, I would say that let's all, give a round of applause for Professor Maya for really thinking about a very relevant topic, and this is the best time of being there. So I would like to do that. So finally, I would let the stage conclude with a few words from Professor Maya, but looking at the interest, I think, Professor Maya, we should have one live session before we conclude this program on SPARC, which is 31st of March. Maybe IIT Madras can host it. We can discuss this offline. But, please, I'll take a few words. Maybe before you, can I just invite Professor Ram Gopal to say a few things, and then finally you can conclude. Is that okay, Professor Maya?
Perfect. Ram Gopal, any comments, Professor Ram Gopal?
Professor Ram Gopal, you're on mute. Okay, so maybe Professor Maya, he could be having an issue with the internet. Yeah, you can conclude.
Time is ticking. It is already past 7, the 12 past 7. So, see, I got nothing much to add. I think Professor Kumar, thank you, Professor Kumar, for nicely summing that up, all the relevant points already. You have done a wonderful job of summing it up. Okay, you have commented on all the talks and all the from where different geographical locations and so on and so forth. Good. So only I wish to say that this is only a beginning for us. CO2 refrigeration is just a beginning. Long way to go. Only with more and more dissemination of knowledge, more and more training, people training, we can go forward. You see, we have actually our system, the system which we are having, it start leaking. There's a crack, and we started, diagnosing it. But okay, fine. How it happened later on, accident took place, it's leaking. But how to stop it? So we found our own method now. So we are very safe. I think successful in arresting even at 130 pressure and 100 plus 120 centigrade instant. The only thing is that Kumar should tell whether CO2 will eat up silicon rubber or not. So if it's silicon rubber, then after 1 year it may leak again. Otherwise, it's stopping. No issues. We didn't depressurize. We didn't dismantle anything. We just could stop that leak, and our people, Shiva Kumar Reddy and our Guchetan says that is perfect. Nothing, no leak, because we could see not even a 1 ppm increase in the sensor. So it's a perfect. So like that we have developed our method. So if something goes wrong, then you have to find a method to correct it. So CO2 is not a big thing now. We have to train the people how to handle high pressure, and we have to develop the system. Hopefully, we will have a couple of demo sites, and then it will pick up. It will be exponential pickup, I am expecting. If one system comes and people see what is the benefit, payback period is less than a year, and people jump on it. That is India is the problem, because nobody will bell the cat. Once people see there's some benefit, people jump, and then it's scarcity. It happens everywhere. Even for our IIT has launched the online course, BSc engineering. Now we don't have, of course, we got enough seats filled, but we don't see any rush. And once the first batch comes out and they are equivalent to our BTech, then there is people jump, because the IIT degree, IIT alumni, anonymous. So people jump. Now at present, people don't see that what is the benefit. Like that, CO2 system will also have a lot of benefit, I'm sure, in the years to come. I have projected 100 units by 2025. When I'm giving a lecture at the Norway conference, my projection was 100 units by 2025. Probably we can arrive 100 units much before that. So with these few comments, I once again thank all the attendees first, then the SPARC management and MHRD for sponsoring this. Probably I don't know whether they will provide us the money or not. I don't know. As of I have to thank them for giving the platform for hosting this wonderful workshop, and all the resource persons who have given excellent lectures. 5 days, 5 into 3 or 5 into 5 plus 1. So 16 lectures they given, and my Dean General GE staff who are given all the support to run it. That is Kumar and Guruchetan and co, and all the PDFs, of course, who are the backbone for this workshop. With this, I think I thank everybody, and have a wonderful weekend, Saturday, Sunday, and thank you very much. If anything has left, you please, if anybody is left for thanking, then I probably somebody can point out I've left somebody, and I thank them also. Thank you very much. Have a nice weekend. Thank you. Namaste. Bye.
Yeah, thank you.